Hey Isaac, we're back on,
All right,
and hopefully now the audio should be good.
cool. Yeah, let us know if there's still any issues. But I guess we'll just try and roll with this. I can hear you just fine, and I think you can hear me too.
Yeah, I
Um,
can I can hear you. I think it was a Twitch bug where the Twitch audio wasn't coming in from anywhere else. So I just restarted Twitch Studio, and hopefully
all
this is
right,
good.
cool.
What I can do, if you
Yeah,
give me just a second, I'm going to quickly.
go for it.
Uh, I think we'll need to rely on Irma for this. Um, let's just quickly check. I'll ask Matt to help us out just a second. Uh, Don? Cool. Don's gonna just take a listen and see if you can hear us.
Cool. All right, so we got three tests passing now. So I guess the next thing to do is to break something else and see if that messes this up. Let's do something tricky, like just make this count off by one.
Yep.
Wonder if we'll catch that.
Yeah.
Yep, we caught that. That's good.
Nice.
Yeah, the length assertion failed, so it's good we have that.
Okay. Hey, Isaac, looks like it's the same thing. Um,
Omortos says,
uh,
"Hey, I can hear Isaac now in the chat."
oh, okay. Okay, cool. Don says you
So,
can hear him now. Okay. Hey, we're
cool.
good. Great.
All right,
Hooray.
I think we're good to go. Thank you guys. Thank you,
Yeah.
Omortos, for letting us know.
Yeah.
Um,
Isaac, do you
yeah,
want to re-sign us in quickly? Because I deleted that previous
sure.
intro. Uh, then we've got it on
All
record,
right.
our log
Um,
stamp.
the Tiger Beetle sessions. Monday, the 31st of January, session 14. Hey, Yarn, what's up?
Hey Isaac, so it feels like we're on the International Space Station yet again, keeping our log of the journey so far, which is pretty epic out in space, whole new LSM tree implementation. So yeah, basically where we're at now is we're just trying to break our segmented array on purpose, inject logic bugs, mess around with it, check that our first test harness is
Yeah.
catching everything. And then today we're going to actually jump in and see if we can do some bulk inserts and removes
Yeah.
now that our audio is back
So
on.
what else
Yeah.
can we break here? Um, hmm. Just trying to figure out what else we should try and break. What if we make, I just want to like put like off by ones in many places. Um, hmm. Maybe like this code's kind of tricky, right? You break something here, I'm sure.
Yeah.
Um, if I just like make this count off by one,
Yeah.
if that fails,
Nice.
assertion failure.
I had an idea too on line 20 downstairs. We could swap the B and the C around so we can
Oh
increment
yeah, it's a
B's
good idea.
count, decrement C's count.
Catch that too.
Yeah.
Just assertion failures. We're not even getting to the test failures. Just
Yeah.
assertion failures.
Yeah.
Um, isn't cool. If we just forget this line, another assertion failure. Yep. What if we mess with the iterator now? Like get this iterator
Oh,
next function
yeah.
wrong.
Yeah.
I'm sure we could make an error here if we like, what do we do? Guess we could forget this -1. We're probably getting out of bounds then. Um, Not sure how to break this code the best. Just like
We
skip
could,
stuff while iterating.
yeah,
And I'm sure we'll catch this, to be honest. But yeah.
yeah,
And that's that where there we actually get to the testing result and verify that they're not equal.
okay,
Or if we start the iterator in the wrong place, that would also be interesting. If
yeah,
we well, I mean we've got asserts like all everywhere here, so it's not gonna be we're not really gonna be able to fix this up. But I'll get rid of like this +1. Perhaps that screws us up. Yep, that does also break things. Of
nice.
course. It's
And
all
I was
very
wondering,
good.
Isaac, if we go up a bit to the top for our iterator, a little bit further up, start node. How do we work with that?
We don't really test that actually currently. We always just pass in 0 or end.
Yeah,
Um, I believe. Because here during verify, we always like iterate over the full range of the array to test it.
yeah.
Um, yeah, don't know if there's a better way we can test that.
Because we don't really have the concept of node in our reference implementation.
Exactly, yeah.
So I guess for start node, it's gonna, hmm,
And we
okay,
could like manually, like in the test, like iterate over the nodes in our array. Then we end up just re-implementing the iterator. It's like
yeah,
we can test that if you like use the same start node. Hmm. So we could do something like where we iterate once, starting like at some arbitrary start node, and you pass in like the last key or the last element in the whole array. And then like verify that you get the same result as if you use it at the first start node and like the middle start node or something.
yeah,
Like compare it against itself kind of with two separate different start nodes that should have the same behavior. We could do that.
okay. That would be good. Yeah, I also realized now that we didn't do testing different start positions for the iterator. Um,
Yeah, it's not really easy to do with a reference implementation.
yeah,
Um,
uh, yeah,
I think I think just testing it against itself would be okay. Should we do that? Just add that to verify real quick.
yeah,
Um,
yeah. I think that would be great. So Omar asks a question. He saw an issue on
yep.
Rafiki where it was mentioned that Tiger Beetle, you can't delete accounts or delete transfers or delete anything or change anything. So the reason for that is because it's um, it's a financial accounting database. So the goal is to provide financial consistency, not just raw data consistency that a database can provide. We want to provide one level higher of financial consistency according to the domain. So what's really important for financial data is that nothing can be changed or edited or deleted. Otherwise, someone could go in and delete some revenue or delete some expenses, and that would have an impact on the audit later, and then the audit wouldn't reproduce. So the reason why Tiger Beetle has everything immutable is because that's what the domain requires for financial consistency. So you can only ever um, post transfers between accounts. If you want to fix that up or correct it or undo it, then you would just post the mirror image, and that way you're always leaving an audit trail rather than just deleting stuff. So it's a bit safer. Yeah.
All
Thanks for the
right.
question.
Yep. So how are we gonna do this? So I guess one way to do this would be to start iterating. We've got the absolute index that we can use, and so I guess we could like initialize an iterator we choose a random absolute index somewhere in our array. Then we initialize an iterator using 0 as the start node. Then we look at like what node the iterator is at. We kind of reach into the implementation a bit and look at what node the iterator is at after it's been initialized. And then we choose like random nodes between 0 and that node to try it. Then we're also still kind of like trusting. I don't see a good way to test the implementation or verify that it works properly because
Yeah.
I think actually, yeah, I guess the only thing that could be is like passing a higher start node is also invalid, we say. So we can't really test that skips data.
Yeah.
Um,
We could, what we could do is in verify, we could iterate the actual nodes. We
yeah,
could,
then we just re-implement the iterator is what happens. Like to iterate the actual nodes, we just end up doing this, I think, right? I guess we could do it
yeah,
without like with a different version, actually, without like the next thing. Let's try
yeah.
that maybe. And so, um, what does this look
Like
like then?
just as a simple case that's not even a loop, we could set,
Yeah.
there's more than one node, we could set start node to 1 and then check what's the first element we get out. Um,
We have to pass in an absolute start index for the iterator though. And right now we pass that in as 0. Um, like what we
okay.
want to do is like choose a random absolute start index and then here in our verify function manually iterate without using the iterator to figure out the maximal start node for that thing, or maybe like the second to maximal. We'll have like some margin of error there, and
Yeah.
then we try and iterate using that start node and compare that then to the reference.
Yeah, I think that's a
So
great idea. I also like
cool.
that we're not trying to get right onto that start node, but just a bit in between.
Yeah, we want to get close but not right on because that's what we'll be doing in practice.
Yeah.
Um, so I think the first thing to do is then pick our random index, which remove already does. Well, yeah, it's this essentially. Yeah. If we don't need this minus count, it's just reference length. I think we might already have in scope here. I'm not sure. No, we don't. Reference to items.length. Okay, that's our index now, and we're gonna start iteration at that index, but we want to just iterate. We want to figure out what node that index is in. And to do that, we're just gonna we're gonna just iterate manually, essentially. So I think we want to say like var node equals 0 or colon 2. Then while node less than, or really, it's gonna be like while index is less than, is greater than, while node is less than node capacity, or it's gonna be context array dot node count. I'm realizing we're just kind of re-implementing the same thing we have in the iterator, but
Yeah.
maybe that's fine.
It's a tricky one to get right, you know?
Yeah, it's
Uh,
hard to know how to test this properly. I think we do have it right, but it's just like there's no
yeah.
really good way to test it, I feel like.
Yeah.
Um,
Me too. Isaac, what if we like use cursor for absolute index? So we pick a random index, use cursor for absolute index to work out a node, and then we
okay,
subtract some random amount of nodes, testing that the iterator still relies on the absolute index
I
above
think
all.
that's good because then we exercise this function a bit more. Yeah, I think that's better than doing this because this is also just re-implementing cursor for absolute index essentially what I just started doing.
Okay.
Choose a random index, then do a const cursor equals cursor for absolute index, index, and then we're just gonna start iteration at that node and compare with our reference. I can
Or I
probably
thought
do you really want to go? Just copying this.
yeah. But I thought what we can do is also tweak with the node we start at. So the start node can be
Indeed.
now.
So
eh,
we have so cursor. We could then well we can make this var then maybe and then kind of take or also just use a new
New one, yeah.
thing on start. No, that's more like SSA form then, so it's like actually easier to optimize and better.
It's better.
Just
Yeah,
and
better.
then
More functional,
cursor.node.
definitely.
We can hear you saturating again. Um,
Okay.
is it so? Yeah.
Otherwise, we could just use uint at most biased and then pass in
Yeah,
cursor
but
node.
if cursor is zero, if cursor.node is 0, then we can't subtract anything. And so instead of branching, we could do this.
But we don't even need to subtract. We just say that the start node is context random uint at most biased, and then we pass in cursor node.
Up to so anywhere below cursor.node. Okay, yeah. I
Yeah,
don't know why
yeah.
I'm doing it this way. Um,
That's just the cool way,
yeah, okay. Cursor.node at most. Then I've got my ZLS updated now, so now we don't get, now we can format and everything is normal.
Awesome. So your ZLS is on 0.9.0 of Zig.
I think so, yeah.
Yeah. Okay.
I think it's ZLS also version 0.9.0, which is kind of weird. They skipped some
Yeah.
versions to get there. So I'm not really sure what they're doing with versioning, to be honest. But it compiles and works. And I
Cool.
got, yeah, a syntax highlighting all still works too with the semantic tokens
We
because I get like it, this, I get like my types highlighted too.
Nice.
Um,
Yeah. We're gonna get a very nice Zig. This is where Zig 0.9 is so great. We're gonna get a really good compile error here if we run this.
yeah, we don't use start node anywhere, of
Yeah.
course,
Yeah.
because yeah. Oops.
It's a good example where we we would think we're testing it and actually we're not because we just forgot to use a variable.
Yeah, because here, I forget the order here. So
So
it's absolute index, then
start node.
that column's pretty unreadable, ZLS. Come on. Start node is second there. So first is the
Yeah.
index, then start node. And then we start in context reference to items from index.
Yeah.
And then that's all that is.
And we've got one bug because I think our index here is can be out of range because it can be at most items length.
Yep.
So
So
we
this
need
should
to
be less than.
yeah. But I think we actually want to rather do saturating arithmetic because now
Where,
if items length is empty, then we've got no items, then we can't go less than 0.
hmm. Yeah, this just doesn't work when we have 0 items. We should probably just have here an if items at length is greater than 0, then.
Yeah. Yeah.
And then that'll prevent that case.
Yeah.
I want to just like kind of group these together
Yep.
and then do that. And then we should really do the other direction as well.
Yeah.
Should we do it with the same cursor? I think we should. Just copy this part now. Here we don't need that. We can just do the -1. Well, actually, no, we don't even use this index. We just use index now.
Yeah.
It was not last on node. It's now start node. Oh, is this not? Is this gonna? We want the other direction though. This cursor and start node are only for the ascending direction.
Yeah.
We need a different start node for descending. Well, cursor is still the same, but we need to calculate start node differently.
Start node
It needs to
differently.
be
Above.
exactly. It needs to be from cursor.node to the maximum to the node count. So
Yeah.
it's just cursor. We want like I really wish there was like a range function that just made this simple, random like a uint range.
Yeah.
I guess you can just add the start pretty easily though. So our
Yes.
minimum is then is cursor.node. So
Is there
a
not one
cursor.
already, Isaac?
There isn't. I've looked sometime recently,
Okay.
and then it's gonna be.
Whoops, sorry. Okay. Just a second.
Go for it. I think is this correct now? We do cursor.node plus at most the node count minus cursor.node.
So node is an index. What we've got on the right is a count. So I think we've got to off by 1 because we're going to add a
Yeah, we
count
probably
to
do.
an index. Yeah. So it should be um,
There should be like another -1 in here, I think.
hmm. So let's say there's only one node in total, so node count is 1. So cursor.node is going to be 0. So the remaining nodes will be 1 minus 0 is 1. Is that correct?
Yep.
And then
And so I think
another
we just need a
minus
-1. Yeah,
to
or give
exclude
us
this
0.
one. Yeah, 0.
I think we do the -1 either inside here or outside. It doesn't really matter.
Yeah.
I think I'm gonna do it with. I think it's just node count -1 is what we want though.
Yeah. We could add an
And this
assert
needs to
there.
start.
We can add an assert that start node is greater than or equal to cursor node. And okay, we can also add an
Hmm?
assert that start node is less than array.node count, just to help ourselves out if we get it wrong, you know.
Sounds good.
Yeah.
Here we need to not use reference to items at length, but instead index +1. Because the first thing we do is subtract 1 here.
Yeah. Yeah. Cool. And then up above, how do we group the iterator? We do it like that. Okay. Maybe we can move the construction of our iterator there. Yeah, like that.
I think this looks pretty good. This is the
Yeah.
only part I'm not terribly happy with, but I think it's all right.
Yeah. So yeah, the maximum index is node count minus one. That's the very last node index. Yeah.
Yeah, cool. That should be good. Let's try it. Unidentified reference. Yeah, I guess that makes sense. Where did I do that though? Here, context at reference. That's still under 100, barely. But
Wow.
U32, U size. Oh yeah, now it's not gonna be under 100. Now we're using. Now we didn't cast it. So maybe we can just do that on a separate line then. Const reference length equals cast U32. Reference items length. Spell everything correctly? I think I did. You went. Yeah, I need to use random, don't I? See how many typos I've made. I think it's a lot today. All right. Passes.
Nice. Hey, awesome.
Cool.
Can we
All right.
we can't break our iterator really. It's not going to show this.
No. Yeah, I think this is just. Yeah, this shows that our starting in the middle works now, which is good.
Yeah. Yeah.
We weren't testing starting in the middle at all before, and we start with random start. This is just a really good test to have, but
Yeah.
doubt we're
What
gonna
if
get a failure here.
yeah, you know, Isaac, where we do our iterator start and we work out
Yeah.
we try to get to the start node. Can we go one further there or something, see what happens if our test catches it?
Um, just to like
In our iterator
you just
constructor,
like add one. Where do you want to go? Like here?
actually into context array iterator, into that constructor where it receives start node.
Here. Just add
Yeah.
one.
Or just to take a look in there and see if we can break it closer to where the implementation is.
I'm just adding one here will break it.
Okay. Okay.
Yep. I just broke it down out of bounds. We can also try like doing a subtract one. Gee,
Yeah.
that won't help this. That could break this one though.
Yeah. Saturating subtraction.
Then we won't get
What's
the out of
happening?
bounds. Oops, that's not the right way to do it. You gotta do the minus first. I
Yeah.
haven't quite gotten used to these.
Yeah.
And that gives us a failure in our verify function in this code. So that's good. It gives a failure
Okay.
right here in
Okay.
this expect equal.
Great.
That's very good. Nice. I think
Yeah.
that's good
Awesome.
now, I think.
Yeah.
I'm glad we found that we could add this test case. That's a nice one to have for sure.
Yeah. Me too. I remember we spoke about adding it and then we sort of forgot it as we saw the first test passing and
Yeah,
yeah.
I think yeah, it's definitely important though, because otherwise we aren't testing the tricky part of the iterator, which is like where
Yeah.
to start at.
Yeah. Exactly. Cool. How are you feeling about the bulk inserts and removes? Have you got an idea?
Um, yeah, I mean, I think we can work through it pretty well.
Yeah. I
Shall we jump
realized,
into it?
yeah, let's
Or
go for it.
have you?
I realized after Friday that I think I was wrong when I said the cost will be the branch. At present, our performance is maybe the branch mispredicts or the branches. I think it actually will also have a performance benefit from the mem copies because it
Yeah, I think that's
becomes,
primarily the mem copies,
yeah, yeah.
especially
Because
when you have
we're
bigger node
doing,
sizes.
yeah, if you've got a batch
You
of 10
do,
to insert,
yeah,
you're
you do 10 mem
multiplying.
copies instead of one mem copy, and so it's a huge
Exactly, yeah.
difference.
Yeah.
Shall we do insert first or remove first?
Let's do insert. And
Insert.
do
Yeah,
you want to do like a new cocoon tab where we just sketch out a few scenarios and say, okay, we're going to insert five
sure.
elements and like different cases. So we're
Yeah,
going to
so
insert to the middle of a node. We'll insert to the
yeah,
beginning of a
so
node and insert to the end of a node.
yeah, so let's kind of like just gonna kind of sketch
Yeah.
out branching logic. Like if all so we kind of like I can just like number out our cases perhaps. Maybe that's better. All elements fit in the target node. That's the simple case.
Yeah.
Then you've got and not all elements fit in the target node, I guess. And
Yeah.
so that means that you have to look at the next node as well. And then, well, actually, do you even look at the next node? I don't think you don't. I think you just split the target node and then have two half nodes. So um, that's the simplest way to do this anyhow. I think
Okay.
that's what we do currently as well. So and
Yeah.
then
Because we
this is
do,
like what we do is then just insert um, do one copy to make space copy the elements into the node. That's the easy case. Then here we
yeah.
have not all elements fit in the target node. I think this is actually because we do this assumption that number of elements maximum number of elements to insert is less than node capacity. It makes it simpler, but here it's not actually that simple. We could make it even simpler by saying that maximum elements is less than half of node capacity. Yeah, this still works with node capacity because we are still guaranteed to be able to fit all the elements in the current node plus the inserted elements into two nodes. We just then split that in half. So
Yeah.
um,
I think
um,
the idea you had where we restrict the size of inserts and removes to a single node, that was brilliant because it it I think it's going to mean that we're going to find our logic is exactly the same. It's just
yeah,
that up till now,
essentially,
it's going to be all the same big picture. It's just that instead
yeah,
of mem copying in a batch of one, we're going to mem copy in a batch of n. So
yeah.
it is going to literally be like 3 or 4 lines that we tweak because of this restriction.
There'll be slight differences. You'll have to have a few more branches because of the case where you're mem copying your items in some to the first node and some to the second node. Because it's the case that like you can have, depending on where the
Okay,
split
yeah,
lies, you can have some of your elements inserted to the first node and some to the second node.
yeah,
But how I think we should do this is
that's
we should just look at these elements in these or examine the elements in the current node we're inserting to and the elements being inserted as one list. Find the midpoint of that list and then split them between
Yeah.
two nodes evenly. Yeah. So I'm gonna list all these steps. So count total. So total equals elements inserted plus elements in target node. First total over 2 elements go in target node. Second, or other. Go in a new node. I think that's all it is. Shall we try and implement this now? I think that doesn't sound too
Yeah.
bad.
Yeah. And I had one more idea is in
Oh,
our bulk API where we say insert elements, we actually allow the user to provide more than a node's worth of elements. And if they do, then we just break it up into multiple insert.
oh, yeah. That seems like a cool idea.
Yeah.
Hmm. Then we don't have to have any special edge cases the API user has to be aware of.
Exactly. Yeah. Yeah.
Cool, I like that. That also keeps it nice and simple. And
Yeah.
so we just do repeated. Yeah, that keeps the logic. That gives you it just amortizes this logic essentially.
Yeah.
It keeps our complexity very low and then amortizes the insert over very large batches potentially. So then we
Yeah.
don't need this assert anymore. We'll just say, yeah. And I feel like we should implement perhaps insert element in terms of this helper function then. So let's call this, well, we're working a new function now. It's called insert elements.
Slice or
No, we have insert
uh,
elements already. This is gonna be the one with that only handles up to node capacity.
okay.
We can
Could
say
it be
insert max node capacity. This is the very first name,
yeah.
which maybe is fine because I don't think we're ever gonna call this except for like once here in this function. So let's just go with this for
Yeah.
now, maybe.
Yeah.
Node pool. Well, I guess I can probably copy these arguments. And here we can add this.
I was thinking also the case where we have to split the node, we could first, before we split, just insert as many as will fit into the current node, then adjust the index. But we can't do the split because then what will happen is the node that we insert is not going to be more than half full.
Exactly, yeah.
Yeah. Okay. Cool.
You
I'm
also
with
want
you now.
you want them evenly split between the two nodes.
Yeah.
That gives you like that
Yeah.
just a very balanced list.
Yeah.
Um, I think it's not also it won't be too bad.
Yeah.
Yeah, we'll see when we get to that part of the code though. So, should we rewrite this real quick to call this in the right way then? So
Yeah.
insert max node capacity elements.
I think we should
Um,
do like just quickly on the name, we should do keep insert elements as the prefix, and then because this is kind of a helper to that, so we could
okay, yeah.
say insert elements underscore batch or max, or I don't know what you think, or insert elements
Most. Um,
at most node to
bound.
at most node capacity.
Or just say bounded. No.
Yeah, yeah,
Or
that's
just
great.
insert
Insert
elements
elements
batch.
bounded by node capacity.
It seems really verbose though.
Yeah,
You can also just call it batch.
yeah, I think that's cool.
I think just doing that. I think it's just better. think I like that because it's yeah. It must be also greater than 1, right? We can also assert the elements. We can insert empty slices. Or do we allow that?
Yeah.
Or
No, we
currently do
should.
allow empty slices. We probably
Yeah,
shouldn't.
we shouldn't. Yeah. And we should check for remove as well, remove elements that we do.
Well, here we assert the count. I think we assert this and remove it. We assert here that there is something to remove. We should assert the count is greater than
It's
1,
greater
I
than 0.
guess. Or greater than 0.
Yeah.
We put that first.
Oh.
Well. Okay. So insert elements batch. We're now no longer 4 elements. We really want a different kind of loop here, I think. We just want like a while loop. Var batch. Batch
Keep
0 is the first batch.
we could keep retaking the slice, but okay, you do what you think.
Yeah, maybe like shift having a slice that gets. I think let's try this first.
Yeah.
Well, batch times node capacity. Or maybe it's just current, and then that's the current index to insert starting from.
Yeah.
Well, then just while current is less than elements dot length, but then we do current plus equals node capacity. I think that works. And then here we insert, it's going to be absolute index plus current. And here it's going to be elements, current, 0 node capacity. This might go out of bounds though, so this needs to be like capped at min node capacity. This is slightly tricky. This is going to be elements.length minus current. I think. Is that all right? I think it is.
Yeah. My feeling is that we increment, like at the end of the while loop, it would be nice to assert and say that current equals elements length. We kind of have a mismatch between unconditionally adding node capacity to current, whereas we take the min within the loop.
Yeah. Not quite sure how to clean that up though.
Yeah. Can we try just below, like leave this loop in place, but just below, try and see if we take a variable slice and say like var batch equals elements, and try and make it that we only have the length calculation in one place.
Okay. this R needs to be like elements dot dot math dot min known capacity element dot elements dot length, right?
Yeah, I'm not sure. I kind of even thought an unbounded, just equal to elements.
Okay.
And then when we reslice it, then
What's our loop condition then? Like, well,
batch.length is greater than 0.
okay. And then here we're gonna do like batch. So I guess it'd be like batch dot pointer plus equals new capacity or something like that. Or just it'd be like batch. Equals elements.
Or
I'm not sure how this works.
we'll reslice. Maybe like we should take a const and calculate the max, the min, so within the loop, we'll say const like new length or whatever equals min node capacity and batch length. Okay, and then at the end of the loop, we can say batch equals batch, and then we reslice it. From new length onwards.
From new link onwards, okay.
Yeah.
Okay, and then what do we call the function with?
Then we'll pass in batch from the beginning, from 0 up to new length.
Batch.
And then we can actually call new length can be renamed to batch length.
We also just call. Yeah. This seems. I think this is gonna be cleaner. Yeah. Except we just need the right name for this.
Yeah. Are you happy with batch underscore length?
But I'm not happy with the name batch in general because this is kind of like remaining actually.
Okay, cool. Yeah. Because I like now that we don't have to get the current position anymore.
Batch length I think is good now.
Yeah.
And this we can go in the loop condition, this slice.
Yeah.
No, it can't
we
because batch length is in the scope then.
Yeah. And maybe we should call batch length, call it batch count, because that way we a little bit not so close to batch dot len.
Sure. Well, this isn't a thing anymore. This is remaining dot length.
Okay, that's also good.
Or yeah, this also needs to be remaining dot length. Just missed those two.
Cool.
Don't have math here yet. Batch. Index plus current. This is also not right though. What does this need to be?
Okay, that's the problem. Yeah.
Yeah.
We
could do
can
pointer arithmetic to find that, but it's not very nice.
we could just track increment our index as we go.
Like how it's another variable for the index. Then you got like two loop variables there, which you only really need one.
Yeah.
I mean, we can also do the same thing here, essentially, where we just here say const or a batch length. We can just, it's the same thing.
Yeah.
Batch length equals math.min node capacity elements dot length minus current. We use that here. Batch length, and then here we decrement or increment.
Cool.
But it's not even really any different. Like that doesn't actually make our loop more secure, does it? It doesn't change the logic at all. It just makes it a little bit more verbose.
Yeah, I think it's better because at the end of the loop we know that current is all the way up to element's length, but it's not beyond. It
Yeah, but it
it
being
doesn't
beyond is also not really a problem.
it isn't, but it just seems wrong that it should go up exactly and then not that anyone is going to come and change this or rely on it, but I think it's better.
Yeah, I
But
just
this
feel like
is
it's cleaner without having, if you don't need the temporary variable, like it's just like you only have like one thing inside the loop then,
yeah.
just the function call. Maybe it's doing too
So
much at once. I don't know.
yeah, what would be good is at the end of the loop you assert that current is equal to element's length. That should be possible.
Sure.
So I think it's better to just do it like this. This is great. Then we can drop that reslicing at the bottom.
Do I mean just to drop this version?
Yeah. And then maybe let's just rename current and call it I, so that it shows
Sure.
that it's some kind of it's an index that we add to absolute index. And then it thins it out. And then I think maybe batch length we can just rename to like batch count.
There's count.
Just count even, yeah. I was thinking that
Where's
too.
batch? I don't know.
Yeah, batch is cool. That's nice. Um, then this is pretty simple.
Yeah, this album probably got on one line even, or
Yeah.
maybe. Oh, it's exactly
So
100.
it does. It does. Awesome, Isaac.
I
Yeah.
kind of like it more and more lines though. Um,
Yeah. Yeah, definitely.
hmm. I still might prefer having this thing here in the loop condition, but I also prefer having it only done once. And so let's leave
Yeah.
it like this.
Yeah.
Okay, that's good now. Let's move on to the actually hard part. So first thing we need to do is
Uh,
handle the zero case where there is nothing in the array.
yeah.
Um, okay,
We could
yeah,
almost do you want to copy our code from below and bring it all in and then we see how we tweak it?
sure, we can do that. So array.node count equals 0. Then we assert absolute index is equal to 0. Then we say node count is equal to 1. We get ourselves a new node. Set counts to 0 and indexes to 0. Then we go into this to split node of full path.
If before we get there, there's just one assert up top we can fix, line 11 upstairs on where we assert absolute index is less than element count max. We can now bring elements length into the picture. So absolute index plus elements length is then less than or equal to element count max. Because when we add the count to the index, it transforms it into a count as well, and that's why it can then go
Yep.
up to element count max.
Cool. All right. Split in a full function probably needs to be changed or gotten rid of or something.
Yeah.
Cursor for absolute index. This is the check that now needs to change. We need to add like the other thing to that. Let's just inline this stuff for now.
Yeah.
And so we can deal with logic there like all at once. Then we can think about factoring it back out if we need to.
Yeah. I think that function is only called in one place anyway. Here.
Indeed, yes. I
Yeah.
don't even know really why we factored it out. I think just like to make it cleaner or
Yeah.
something. I don't know. Unless we already have this
We.
assert. That's redundant. I think we actually was. I think
I
it's
th
because we've had like a block here. We had like const cursor
Yeah.
pulls.
Yeah. That is
Then
why.
we might reassign it. Do we even want this here though? That's the question. Um, so after we do this, what we do before in the old version is that we do. But you see here now we don't have the same code path for both these cases, where we can just insert the single element into this one node. Because there are cases, sometimes if we split the node, we've got to then insert part of our batch into the first node and part of our batch into the second node.
Yeah.
And so we can have the same code path for these two cases now. So I think we should just kind of, I don't know, I feel like it's not helping us that much to copy this code. I think we should kind of just refer to it, but not copy it directly.
Okay.
Because I think,
Cool.
yeah,
I'm with you.
referring to I think will be good. But here, yeah, this is just the trivial case. And now we want to check if all of our elements fit into this node. Oh, so to do that, we need to do the cursor for absolute index. Absolute index. Absolute index, come on, there we go. Oh, this is, cursor equals array dot for absolute index, okay. And now this is going to, now we have a node we can look at. So we can say if cursor.node equals node or counts
Array.counts for cursor node.
Cursor.node, comparing this with elements.length.
So array counts plus elements length is less than or equal to node capacity.
Node capacity, yeah.
Yeah.
Dynamator. Hi, Dynamator. Welcome to the stream. I don't think I've seen you around here before.
Yeah. Good to see you.
We're currently working on our segmented array, kind of like an unrolled linked list. And so this is like part of our LSM tree implementation. Yeah, so we're now writing a lower level data structure that's part of our in-memory metadata storage for the LSM tree. And because we do like static allocation up front, we need like a nice way to split this data into like little blocks we can allocate from a pool allocator. And so an unrolled linked list or / segmented array makes sense for that. But we also want it to be fast. So now we're doing like a batch insert method that will amortize the copies. What are your atomicity desires? I'm not quite sure what you mean with that. I guess that's kind of tying into like how inserts become visible across the LSM. So we've got like a super block that we kind of like do snapshots with. The locks.
Where are the locks?
Yeah.
Yeah.
Where are the
So
locks?
it could be. Do you mean atomicity like in terms of memory or storage or multi-threading?
All single threaded.
Yeah.
And one reason we can do it all single threaded like that, yeah, is because we have an incremental. We do incremental compaction instead of like having compaction doing running continuously on a separate thread. It just kind of happens incrementally at every tick of our BR protocol.
Yeah. Yeah. So
So we
and
don't even
the
do
reason,
multi-threading.
yeah, there's no multi-threading at all. Yeah. And the reason is because that's also why we're writing our own LSM tree slash forest. It's because if we were to do multi-threading, it would make autonomous testing more difficult because then we wouldn't be able to use like the techniques that Foundation DB use, where you can deterministically fuzz test your whole control plane. And if you get a bug, you can just replay it and everything is always deterministic. So that's why we don't do multi-threading. So that's why the control plane is single threaded, just to give easy control flow. Yeah. And also because using IOU ring, then we're kind of relying on the kernel to do the heavy lifting,
Yeah.
multi-threading there for the data plane. But all this stuff here is kind of control planey. So I don't know if it benefits too, like the segmented array, I don't know if it benefits too much from multi-threading because we're we're keeping track of table infos here for the LSM tree manifest.
Yeah.
And one table can have 64 megs of data already. So we're putting like a 64 byte metadata into this structure, but that represents a whole lot of work that has already been done. So which
Yeah.
which is more of the data plane. Don't know if that makes sense.
Yeah, we definitely have been trying very hard to avoid needing to do any multi-threading because it's just so hard to get right. Um,
Yeah.
and we don't think we need it, and we're actually pretty sure we don't need it.
Yeah. It's working out really nicely not to think of compaction plus have the dimension of multi-threading. Yeah, so will it be
Yeah.
outside of Tiger Beetle? Sure, it will be. So you'll be able to
It has
use,
some strange properties, perhaps, though. But yeah, we're doing some interesting things. Um, like for example, we only kind of use like fixed size data structures, so it's not just like a standard LSM tree, just use like a byte array key and a byte array data. Um, we've instead kind of made it like kind of adapt to your use cases, and so instead of having like one LSM tree, you've got an LSM forest, and each tree in the forest stores a different type of data. And then inside, it has to be a fixed size item or data struct or whatever. And so we have
yeah,
like one tree for accounts, one tree for transfers, and then other trees for our indexes of these, for like the secondary indexes for these structs. And that gives
yeah,
us some nice properties because like you have, it makes queries faster because there's less data to look through, essentially. If you know the thing you're looking for is an account, you go straight to the accounts tree and then you only see other accounts. You're not going through all the data you have in your whole system. Um, and it
yeah,
makes this, we don't need to store like item length on disk, so it makes our data layout much more compact. You're not now storing the length of every key and datum in your LSM tree. Yeah, I mean everything we're working on really is definitely like possible to use it outside of Tiger Beetle, but it will be like somewhat special case to our use case. But for similar systems or systems with similar requirements, then it'll be very useful outside of Tiger Beetle.
yeah,
Um, yeah,
yeah. And it's good foundational properties that it gives you because you get a LSM tree, you get fixed size keys and values. But it isn't really a limitation because if you need different types of keys and values, you just have different trees. And one tree
yeah,
becomes cheap enough that you can now have many, which opens up, you know. And
yeah.
what's
Well,
pretty
we don't yet
cool,
dynamic sized values will be a limitation for some systems because they want to store like variable length things in their
yeah.
database, and we don't
But
allow
for
that
this,
currently,
yeah,
or
for
for
this
Tiger Beetle
level,
ever
it's
probably.
yeah, we don't. But for this kind of foundational level, it's actually not a bad idea to have fixed sizes because, for example, like Foundation DB's got very strong limits. So I don't know what they are exactly, but it's something like you can, have a write transaction, but the key is limited up to this, or um, and then those
Yeah,
become like your building blocks for application stuff higher up. So if you had variable length data, what you could do is just make your value like max 255 bytes, and that's it. So if you're storing like usernames that people can edit, you basically putting a fixed size, but you give them a little bit more than they need. And then you can manage the length prefixes at a higher level. But yeah, so
Yeah.
targetable you can, but also the other nice thing is that these, because the trees are now so cheap, you can have many of them. And the huge advantage of that in the context of LSM trees is that now your data distribution is you're exploiting the performance characteristics of that according to the actual data distribution. So if it turns out that your application is generating loads of accounts that are mutable, or it's not generating, for example, in Tiger Beetle's context, you don't have too many accounts, but they're mutable, so they're thrashing all the time and you're updating their balances. Now it's pretty good still because you don't have that much accounts. You're changing them a lot, but you're still getting nice sequential write throughput, but you're not really paying a heavy write amplification cost because you're not going through all the levels of a big LSM tree. And then all your transfer data that's immutable, again, there you're just appending that sequentially to disk, but you're not now mixing up transfers with accounts and having to pay write amplification. So you naturally exploit how the actual properties of the data by splitting up the data into different trees.
All
And
right.
then, yeah, so the other thing is like it will be reusable, but also with consensus. So this is actually like a distributed LSM tree. So you get automatic high availability across a whole cluster, and it'll be pretty easy.
Yeah, I mean, you can
Uh,
also, I think, rip out the consensus part pretty easily if you want to, but
yeah,
it's definitely going to be deeply integrated with our consensus algorithm and also deterministic, which is
yeah.
a big, it's just critical
And
for the consensus to work
yeah, you don't
for
actually need
us.
to rip out the consensus. You just say that your cluster is a cluster of one, and then you've instantly got a
Okay, yeah,
single node
I guess,
cluster.
yeah,
And it makes sense because the consensus log that you use for consensus, when you're a single node cluster, that just becomes your write ahead log that a single node database would have anyway. So we're actually sharing the database write ahead log is integrated with the consensus log. It's one and the same. So there isn't really a disadvantage. Um, yeah.
yeah, cool. So I've got
I,
this case done, I think. Now we just need to
okay.
update counts. The first thing we do
Isaac,
is we make space for the elements we're
would
inserting.
you would you mind just one more, like just before we come into this, could we jump into main.zig, like where we construct the
Sure.
type, the replica type?
Yeah, this is our replica type. It's just kind of generic
Yeah.
over all these things you can switch out. So you've got like the replica actually isn't aware of any networking at all. It just takes like a generic message bus type, and you can pass in whatever state machine you want to do your consensus on, and then some way to store data. It could be in memory, it could be on disk, it could be pretty much whatever. The LSM tree will be then part of this, or part of the
Yeah.
state machine, I guess. I'm not sure exactly how we'll pass that in here.
Yeah, the
And then the
LSM
clock.
is actually the LSM is part of replica, so it'll all be internal. So you don't even need
Okay.
to know
Well,
about
sorry, we need that for the. Okay, yeah. So
yeah,
LSM will just be part of replica.
yeah.
We'll have
And
to
then
figure out how
state
that
machine
like works
is
out with the state machine types.
yeah, the state machine
Yeah.
will be able to like query the LSM tree to do lookups and range queries and things. And the state machine is just
Yeah.
your own function, so you can just define your own like commands. Like you can think Redis
Yeah.
commands, and you can just put them all in your own custom state machine, and have distributed Redis
You could
with
like
nice
kind of
LSM storage.
compare timestamps, commit, like create accounts, create transfers. This is the only place where there's actual business logic for your system
Yeah,
in the state machine.
yeah. Like if you want to jump to back into the state machine into create account, so this
Yeah.
is our accounting logic, but you could literally just change this to anything you want. So there's very little, all the work of making it custom would just be in state machine. Everything else would just work because all the distributed principles are the same. We just take the whole design of a replicated state machine
Yep,
Yeah, thanks, Ozzy. Thanks for the
no
question.
problem.
Yeah.
All right. So first thing we do is like make space for the elements we're inserting. This is the case where all of our elements fit into the target node. And we just first do one copy, shifting the elements already in the node to the right to make space for them. Shifting from element relative index elements length elements to relative index plus elements length. Because then we have elements length slots that are free, which we can then copy the actual elements into.
Yeah.
And then we need to update counts. Whoa. Sorry. Array.counts node. Yeah, this data structure we're working on right now is for the in-memory manifest. This kind of like indexes the on disk chunks. Like we have tables, what we call the on disk um, data things, the data blocks. The tables are variable size, and they'll be at different sizes at different levels of the LSM tree. But we also need a way to go from from a key in memory to the correct table on disk, and that's what this structure will do. And so the segmented array is one of the building blocks of our in-memory manifest that then takes you from a key to a table on disk. This is an on-disk an on-disk LSM tree, to be clear, but you need to store some data in memory to be able to query the on-disk data efficiently.
So we basically
And the
need to
LSM
know
trees, like yeah,
for a given
the point is
key
definitely to reduce
which
disk writes. Yeah,
yeah, for a given key, which table on disk might contain the key. So we've got like 1 million tables, we've got 64 bytes of metadata per table. All that metadata this is what we're keeping in memory. So the segmented array allows us to go and find which table on disk will have the key we're looking for. Yeah. So yeah, the LSM tree is for our on-disk storage, but you've got physical on-disk storage that's addressed by the LSM tree, but the LSM tree also needs in-memory bookkeeping data to look stuff up. So this isn't for level 0. This is actually going to be for all the other levels, because level 0 is a special overlapping level where the table infos can overlap. So we're still getting to level 0. This is more for like the million, tables, the big tail, long tail.
disk length, disk pointer, greater than source pointer. Yep, that needs to be copied backwards here. I had that wrong.
Yeah.
Then here we're updating the pointer, then the count, and then also the indexes of the following nodes. So this is now all done for that path.
Yeah. So we're gonna
That's the easy path, though.
yeah. So everything fits.
It's not just level 0. This is indexes for every level of the LSM tree. The actual data we're storing here is just metadata about what tables are on disk. It's not the actual data it's not like the actual data that could be queried. It's just like the start key of the table, or the minimum and maximum key of the table on disk, and plus the location of the table on disk, essentially, plus then some snapshot information.
Yeah. I think for our copy backwards, just to understand
Yes.
better, what we're doing there is we're saying the elements that we are about to overwrite, let's shift them.
Yep. It's basically just moving the elements that are to make space for the ones you want to insert.
Yeah.
Because we've checked this condition here, then we don't need to do any more bounds checks because we know there's space to do
Yeah.
this successfully.
Yeah. Cool. And we must do copy backwards, otherwise we'll be overwriting some of our source data while we're copying.
Yep.
And then we want to copy into the pointer at relative index up to element's length.
Oh, you
Should
know
we
what? This
not?
is wrong, isn't it?
Yeah, yeah. Then it's nice and symmetrical.
It
Yeah,
should match this exactly, because that's where we copy out of. Now this is where we copy into. Cool.
yeah. Then we update the count. Then we
And then we
go
update
for
indexes. Yep. Thanks, Dynamite.
Awesome.
Cool. Now we need to do the tricky case where we need to split the node. And so I think split node we can just call, that doesn't need any changes because that just does the splitting. That's the wrong function. I wanted to look at here in split node of full, we then just do split node, then we do cursor for absolute index again. Okay, so we just want to do that kind of. In split node, we'll just take a node to split it and then leave it empty, I think. Oh no, it moves half the things over. We don't actually want to do that because we want to avoid that copy if we, yeah, I should probably swap to absolute line numbers. What's the, there's highlight global number lines. Yeah, disable. I'll do that later. I actually need to tweak my config. I forgot the name for that off the top of my head. That's a good point, though. I probably should have done that a while ago.
Hey, Isaac, I was
So split
wondering,
node, I think.
here's an idea. Like, what we could do is we could do something crazy where we say, like, insert elements batch, where if we can't fit it into the node, then we split the node and then kind of split the batch also, so that we're doing two inserts. And don't worry if we do a bit of extra mem copy.
That's
But
yeah. That's not always gonna be the most efficient though, I think. I've got on-stream Twitch chat on my other monitor, Darnimator, just through IRC. I haven't bothered to set up Bork. Maybe I'll do that at some point.
we're getting there. We need to kind of figure out how to put Bork like onto the whole overlay, you know?
Yeah, I'll just put
I
it. I'll
guess
just
you,
put it on my screen somewhere.
yeah.
But
Let's just
do we really need it
like,
on stream though? Because I mean, I've got it on my other monitor, and you've also got chat on something you can see.
yeah. The reason to Borkify is that then like you've got it recorded on your YouTube videos as well. You've got all the chat history in the
I mean, I can
yeah.
just like move this IRC thing over onto here. Well, wrong direction. Now we got Twitch chat, kind of.
Yeah. Yeah.
It's kind of small though. It's probably not at all readable on the video, so maybe we should not do that.
No, you can see it.
Is that legible?
Yeah, it's cool. It's coming through nice. We could
We can
improve
go with
it.
that then.
Yeah, sweet. Is it possible to get rid of the first column in the IRC so we can move it a bit more to the right?
I don't know. I don't know if off the top of my head how to hide that in WeChat. Maybe we should just come back with Bork and properly set up next time and leave it off for now.
Yeah, cool. On the right is good like that, and then
I was just gonna get rid of it for now. But how you realize?
Yeah, I agree with you. We'll bring in Bork and just riverize it, put it on the right.
Yeah.
Yep.
Cheers. Follows, subs. Yeah, I don't get follows or subs or anything in the IRC chat anyways, so I think we should just switch to Bork next time and I'll get that set up.
Yeah.
That would be nice to have.
Yep. So that idea, like to simplify, does it help us or not really?
I'm not sure. I think I'm gonna I'm gonna just keep inlining stuff so we can know, because we don't want this copy. Here's what I'm thinking about
Yeah,
right
yeah,
now. So we no longer this now could be doing an extra copy that we don't want,
yeah,
because um it could be that we're inserting more than half a node of elements, and so in that case, doing this copy would, yeah, it basically would it's just an extra copy that's not needed, because we then have to copy this
yeah,
data again to make space for the elements we're inserting.
yeah,
Um, and so insert an empty node out we can still use, but the rest of the stuff, not really. So insert, yeah, so here we are. We got the split node stuff. Or node, just less than a rate at node count. I feel like we should probably factor these out into functions at some point, but I'm just gonna keep it like kind of messy until we've got a
yeah,
better idea of the structure we want.
yep.
Um, I'm just gonna delete those asserts for now too. Well, yeah, I mean, we already kind of have them, I suppose. But I guess we could put them like after this.
Yeah, we can always come back and then
Uh,
compare the two functions and
hmm,
check that we're getting the same asserts.
yeah, and so we actually, yeah, this assert is now not actually right. This doesn't even make sense. 'Cause that was before we only split a node if it was actually completely full, because we couldn't insert the one element we were trying to insert to it. So new node plus cursor.node plus one, node plus one. Then we insert empty node at node pool new node. Yep. We take our half. Oh, actually, we don't care about halves yet. What we want to do is kind of divide our entire data in half. So I think what we want to do is add. This is now kind of our entire data. Is these two things added together? And
Yeah,
so I'm just gonna call this like total, make it a constant. Total. That seems like a good idea to you.
yep,
And then we can use that here and also in the asserts below. So now we can also like assert that. Well, no, we can't really assert anything extra there, but we can use here total instead of node capacity to get half. And here, now we can't really do this, can we?
no,
No. So we'll just have to deal with
because,
that then. We'll get it right though.
yeah, yep.
It won't be that hard, I don't think. Anyhow, so we got pointer, new pointer. And this should be cursor.node, I guess.
So we do know that we only need to insert at most one empty node. That's all we
Yep,
will have to do. Um,
yep.
I
The
was
tricky
wondering
part
if
is
we,
finding out.
yeah, I was wondering if we couldn't try and maybe it's jumping too much in one go, but if we could have some approach where we use like a single code path where we always doing the mem copy, although sometimes it sometimes is like a zero length slice. So basically, if we go up a bit, this case we've already handled where the total fits into one node, we could kind of rewrite this one so that it works across two nodes.
Can we write
This
this
is
one
like,
first and then compare them? So I think this one's going to be more complex than you think.
yeah, yeah. Okay. So it's kind of like you've got,
Um,
let's imagine we're always splitting. So you've got one node,
yeah,
there's existing data that has to be shifted, whether it's going to be
yep,
shifted in the node or into a new node. Um, so I'm just thinking maybe the end result could be that we've got like just a single
yeah.
code path. That's actually pretty
Perhaps.
simple.
I think this is going to be there's going to be more special cases here. So
Yeah.
um,
Yeah. Yeah.
I'm gonna delete this stuff for now because this is not necessary yet. Or this stuff is just gonna mess us up for now, I think. I'll comment it
Yeah.
out maybe. Okay. So the first thing to do, I think, is to see if the data already in node is greater than half. Um, so if the data in our node currently is greater than half, we need to move that data like to the new node.
Yeah.
Um,
We need to
so
move existing data.
well, so there's two things we have to do. We kind of have to distribute. We've got like a whole chunk of data that's got we have total is the number of elements we have across the data already in this node and the elements we're inserting. The problem is that they're not in the same slice, and so we need to at one point insert the elements we're inserting into this slice of data in the current node, but also then distribute that or split the whole range of the whole total number of elements evenly across the two nodes.
Yeah.
It was like they're doing these two things at once, and just to reduce copies, because if we do them separately, we're doing redundant copies then. Um,
Yeah.
so one of the cases here, um, so I guess one case is the number of elements in the node is less than half, which means we don't need to copy anything out of the node. Oh, well, also depends on the relative index though. Maybe that's the first thing to look at, is like where the relative index is
Yeah.
in the
Compared to
data.
this
So if the
split
relative
point.
index is less than half, then we need to move. Yeah, I think that's what we do. We say the first target is like if relative index is less than half. Um, we're not relative index. This is the absolute index really, but it's the relative index for now because we're still looking at the first cursor.
Yeah.
Of index less than half, then um, then what we need to do is copy data from the first node to the second node, to the correct place in the second node, where we'll then stop copying the elements data into.
Yeah.
So that's gonna be a little bit tricky to compute, but we can do that. We have
We
everything we need
could
to calculate that, and so
we
we'll
could
just do
also
one
take
copy of this initial data.
we could take a look at split node if full and just add some kind of offset to that because that is going to split the node and move the data across. And then we just need to look at that
You know,
logic and see how we adjust it.
it's
That's
right
it.
here.
Oh, okay, cool. Thanks.
This is the copy.
Okay.
It's a little bit more complex than that.
Yeah.
Um, so now we're gonna copy. We're to copy is like I'm just gonna grab like mem dot copy key. We're copying into new pointer from pointer. This doesn't actually need to be copied backwards because they're different pointers. I realize,
Yeah.
but maybe that's
Yeah.
fine. Um,
Isaac, I was wondering, like, maybe we should take a step back and go to the whiteboard and just like visualize it so we can see um,
sure.
where half might be, where relative index might be. I don't know if that will help.
Yeah.
Uh,
I think I've got a pretty clear picture in my mind how this works out, but if you want to
yeah,
draw it, that's fine with me.
cool.
Um,
It would help me also.
um,
A part of me
right.
is thinking like we could try and treat it as like virtual memory. So where the nodes are doesn't really matter. But I'm with you that we need to
Okay, so here we've
calculate
got
compared to
node 1
the
maybe,
split point.
and node 2.
Yeah,
Then we can maybe have, see we're like a little bit over, so you've got like a bunch of items in here.
yeah,
This me some very rough drawing. Um, this one is currently empty because we just inserted it. And say we're trying to insert like, I don't know, Maybe red's a good color for this. These are the new items coming in.
And maybe
I
they,
probably need a bit more. I
okay.
don't know.
Yeah, that's cool.
Not sure. You can tell me if this is not being helpful or not. But so
No, it
the first
is.
thing you
It
do is
is.
like take off the like these items here and move them over to here. Like not at the start of the node, but rather after at the point where there be then space to put in the items from this thing part that we need to. And so we're
Yeah.
copying. Don't want to copy these more than once. And so what we want to do is calculate where in the second node do they need to be copied to. Um, Excalibur. Is that even fancier? Maybe we'll stick with this one for now since we already have something drawn here. Then we'll go with that one
Yeah.
next time.
Yeah.
Um,
Awesome. We were actually looking for another tool, eh? We were thinking,
this is just the first one I happened to find when I was
uh,
looking for one,
uh,
and it's
mm,
kind of like googly web stuff.
yeah,
Um, Not ideal, but it works well enough. Anyhow, so that's kind of this case I'm looking at right now is where we need to copy these things to make space for these to be inserted into the first node.
and
Um,
that's going to be
there's another
the
case.
purple stuff that we're selecting there. That is everything
Yep.
from relative index onwards. That's
Yep.
so we've got to calculate like what's our source buffer. That's pretty easy. Everything from relative index
Yep.
onwards. Then we need
Harder,
to
harder, a little
figure
bit
out
harder,
our target buffer. Where do we start? Uh,
and that's going to be half minus this part. Then that's yellow now. Oops. That'll be goes then we subtract that value from the total number of inserted elements, and that gives us the index into the inserted elements where we then, yeah, I mean, there's just a little bit of math to do there, but it works out. We have all the data we need for that, and we just need to write that in
yeah,
code really, rather
yeah,
than drawing it here somehow. That's one case. And the other simpler case is when you just need to insert after the end of this. So the other case is where your relative index is like here. And
it's
so you're
still
kind of inserting
before the
after all the stuff in this node. And so you then insert a few of these into this node perhaps, and the rest into
yeah,
this node. Or you
yeah.
need to copy a few of the purple ones to the second node and then insert the rest of the red ones to the second node.
Yeah.
That's another case that can happen.
I was trying to
So,
think of like a strategy that could help is if we don't, I, I don't know if we can use it, but if we think of just purple and red and think of it all as like a virtual buffer and not
that's
not think
essentially
of
what
the
we're trying to
underlying
do, yeah.
nodes.
But the
Yeah,
problem is that they're not all in one buffer. And so,
yeah,
and we don't want to do
yeah,
unnecessary copies.
yeah,
How much, are you cool just like start going through the code again? I think
yeah,
this
yeah,
is
yeah, yeah.
easier to just keep stepping through.
Okay,
So cursor to relative index less than half. This is the case I outlined here where we want to copy these things to here as the first step. And so the it's pretty easy to do cursor dot relative index, and then this is going up to the current count of the node. So um, array dot counts node or cursor to
yeah,
node.
yeah. That's it.
Okay. I've oh ZLS is just being slow to update. I feel like new ZLS is slower than old ZLS used to be, but I could be imagining things. Um, and this is
Shall
going to
we
go to new node.
call that B pointer and C pointer so we can see the where
Like
they
we
are
did down
next to each other?
below. I feel like we're
Yeah,
not going to have an A point. Um,
no, we can do A and B.
yeah, right now we use kind of new node and new pointer. I think it's fine with me like this for now, to be honest. I'm more concerned about the indexes.
Okay,
Um, this is going to be the first thing we need to find is how much space is left in this buffer. Um, so that's going to be array that counts minus relative index. So kind of like how much space you're copying out. Um, increase space in. Well, maybe I'll just like, I'm gonna call it X for now. We'll find the proper name for this in a second once we get the steps kind of done. But the first thing I want to do here is do array counts node cursor.node node minus cursor.relative index. Okay, and then so that gives us, then we can subtract this from elements.length, I think. What we want to do? No, so we want to do like half minus this. Shows us how much data we need to add to the first node. So half minus this is the missing data from node 1. After we do this copy, the elements to node. I think A and B is actually better, because I can call this elements to A, and then we can also have elements to B.
And you can also see then, you can see which is on the right, so B is after A. But I had one idea to help us with the arithmetic here, is we could do like Ramsey or Apache Dussault's trick, where we do little examples where the numbers are very small. So let's say that a node only contains 4 elements or only contains 2 elements. And then you can actually work through all the cases and then check that we could do just do a cocoon tab.
I'm doing all right with this so far. That'd be a good way to check it once we like got it done. But
cool.
I'm not sure I need to just find it in the first place.
Okay, then I'm happy if you're happy.
So we have the number of elements we're copying to A. Then we can subtract const elements to B is then elements.length minus this. Length minus elements to A. And now we just copy this from new pointer elements to B. So this is already correct now for this copy. We could then we could try and calculate the end bound here, which is going to be this value here, if we want to like get the bounds checking, just to double check our math. So this is this like kind of like 2 copy here or something. Maybe we don't need that. I don't know. I can also just put it in line. Or I think like that works.
Have we
That's
got
correct.
a thing? Have we got an overflow if the midpoint changes, where we calculate elements to A? We're saying half minus. I think we need to use some kind of absolute distance.
This is always going to be positive. We know the relative index is less than half. We actually didn't check if it's inside. You're right. We're missing something here. We're missing the check to see if counts is greater, if relative index is less, but it has to be less than counts too, because it's indexed into this cursor. So this is going to be 0 greater than or equal to 0.
Yeah, that's fine. But I'm thinking where, like, what could happen is A could be less than half full, but what we're inserting is more than half, or A is more than half full, but what we're inserting is less than half. Like if it shifts based on where the half is. If the half is underneath the old data or if it's underneath the new data.
Yeah. Here is the case that it's underneath the This is where the half is inside the old data. Or, no, not really.
Yeah.
Yeah, you're right. Something's still fishy here. Um, is this the right thing to subtract, actually? This is... No, it isn't really. Um, Actually, this should just be half minus relative index, I think.
Yeah.
Relative index is the number of items that are staying in the first node that don't need to be copied at all,
Yeah.
right? And so
Yeah.
this is then the number of elements. Um, yeah.
That's a good
Well,
explanation. Like relative index, anything below that isn't being
won't
moved.
be copied. Yeah.
But I don't know if that's true
The problem.
because I don't know if it's true because relative index might be
Greater than half, but we just checked it here.
okay. Okay.
That this is the assumption we're making is if relative index is less than half.
Okay. Okay. We're only dealing with one
Yeah,
half of the picture here, like in this branch. Yeah.
exactly. And then
Okay.
we'll deal with the other half later. But you're right. That is like I think this is like kind of the case where it hinges on like the big differences between what you do is this check.
Yeah.
I think that's also what you were getting at here.
Yeah.
I think there's one more tricky thing here though. Um, Relative index is less than half, but hmm, elements to A correct. I'm not quite convinced about this yet. Yeah, it's got to be correct. Let's let me draw this out maybe one more time.
I was actually
Should we try this
thinking
new one?
maybe it's easier if we do cocoon and we do like a simple notation like we did for the manifest iterator. Just we can use something like xxx underscore that shows you a node that's got three elements with one free slot. And then you can use
Okay,
like
so
a
like
pipe, yeah, exactly like a square bracket. That's now where node capacity is 4, and we've got three things in. That's it.
node
Yeah,
capacity is 4, and then our new node is then going to be just like
yeah. And
empty
then we
for
can
now.
show we can above that we can show different places where we'll insert y. Like we could insert y at index 0, index 1, 2, or 3.
We're trying to
Uh,
insert like say we're trying to insert like a batch though, right? We're trying to insert like 2
mm,
or 3 Ys, say.
yeah,
No,
yeah.
we want to insert 3 Ys at index 2.
Maybe two y's is good because we can move that across
Okay.
more.
Well, then it doesn't split evenly, but maybe that's fine. Maybe that's actually better.
Yeah,
Um,
yeah,
so what we want to end up with is um, this, I believe. We insert 2 Ys at index 1. Um,
yeah.
and so that means that our relative index will be 1, which is less than
Mm,
half. Half is going to be 2 here.
mm.
Um, Actually, then we'd actually end up with the x with this. We do the rounding the way we've got it right now. Oh, I'm doing the wrong thing. So my fingers on the wrong keys. This is what we'd end up with if we have the rounding like how we have it now. Um,
Yeah, because we're gonna do flooring division.
yeah, and so relative index would be less than half, and so we copy this x, or these two x's to here as the first step,
Mm,
and then um, half is going to be 2, and relative index is going to be 1. So this is correct. Then elements to A is going to be 1, because 2 minus 1 is 1. So we want to put 1 y there. elements to B is then elements.length, which is 2 minus elements to A, which is 1. So that is also then correct.
Shall we,
Then we copy
can
from
we
pointer relative index, or
can
the
we
relative
copy
index
that?
is going to be 1.
Shall
Sorry?
we copy can we copy that logic to be in the same tab, and then we can just give some and say like relative index equals 1, and then solve it all right there. Or yeah, put it here
Okay,
even
like put it
better.
here or what?
Yeah.
Whoa, that's not what I think.
I thought we can, yeah, let's do the example right over here in the code. Yeah.
Then we got cursor relative
So
index
we're
is
saying
1.
index is 1, and the halfway point is going to be uh, what is it? It's going to be 3 plus. How do we work out total? Yeah,
It's 3 plus the 2 thing y's we're inserting, so
2.
5.
Okay, 5 divided by 2 will be 2.
So I'm happy. This
Yeah.
seems good, except for this. I'm not sure about this yet. This is going to be 3. That's right. Cool.
So
Yep.
Isaac,
That seems good to
can
me.
can I step through it just to understand better? I'm
Go
still
for it. Go
catching up.
for it.
Okay. Okay, cool. So half is going to be 2, then 2 minus 1 is 1. So we want to move elements to A is going to be equal to 1. Is that correct?
Yep.
Okay.
There's one y that ends up there.
Okay. Okay. So elements refers to like what we're inserting, like it corresponds to the actual
Yeah,
elements
elements being
variable.
sent to A, or elements being sent to
Okay.
B. I'm not sure. I think the variable names are pretty decent. If you have any
Yeah,
suggestions, please let me know.
they're pretty good. I just missed it. I was thinking in terms of what was existing data. So,
Yeah. These are
but
these are the counts of the things we're inserting. So these are the y's going to A and the y's going to B.
yeah, that's
Um,
perfect. Yeah, no, that I mean that makes sense. It corresponds to elements itself. Okay, so elements to A is 1, and then elements to B is going to be elements length, which is 2 minus what's going into A, so that will be 1 as well. Then we're going to
yep.
do, uh, we can rename new pointer to be B pointer. Done. Can we do
Oh
that
yeah.
in our mem? Yeah, B pointer, that's our target. And that's going to go from elements to B. I think that might be wrong. We want to actually we want to start from the count of elements to A. That should be our starting.
This
No.
is the place
Okay,
we're
no.
copying
No.
to.
Yeah,
And so we
okay.
want to. We're copying these x's. We're copying these two x's from here to here. That's what this copy does.
Okay.
And so we want to start after. We want to leave space for the
After,
elements that are being placed into B. And so that's why we started
okay,
elements to B here.
perfect. Yeah, okay, that's perfect. And then we go to array counts, which is the count before we did the insert, which is 3. 3 minus 1 is 2, and we want to copy 2. Those are all the things that are after
This
where
is
we're
wrong though.
inserting.
This should be. Sorry.
Yeah, it
This
should be
is
like
this is
that.
a count, not an index, and so it should be like
Yeah,
that.
yeah.
Though we don't even really need this. I was kind of. I almost just left this off. I think it kind of
I think
distracts a bit.
it's it's nice to show because we now saying you can only copy into that much space, you know?
Yeah, but it's also exactly the two bounds we have here. Like it's completely redundant
Okay,
with this. And
okay,
the thing will already assert that there's enough space in the destination for everything in the target. And so,
yeah, okay,
yeah.
cool. Can drop it then. Yeah,
I think it just kind of makes this code too noisy, and it's better just keep it simple, because then you
yeah,
can focus more on what's actually important. Because
yeah,
it is kind of tricky.
yep. Okay, yeah, I'm with you. Then here. we're going to copy from a pointer, which is from relative index, and which is those two x's there,
Yep.
onwards
It's
up
this is
to,
we're starting at this index and we're doing 2 elements.
yeah,
Well, we're stopping at the count, which is going to be 3, and so it's going to be these 2 elements. Yeah.
yeah. And then we're passing a count in on the right-hand side.
Yep.
So we're
Well, count will
saying
be
3.
well 3.
Yeah,
So this is 0, 1, 2, 3. So we stop there. It's exclusive, and so you end up copying these 2 elements, and
yeah,
then placing them starting from elements at 2b, which is index 1. And so you start here and you place 2 elements. Let me do the
yeah.
other copies now too, if you're
Do
ready.
Yeah, yeah. I just wanted to ask, should we do like a double slice there when we bring in the count, like from relative index
No,
onwards?
because this is correct like this. Um,
Of course, yeah.
yeah, this is the count
Otherwise it would
inside
be
the
wrong.
node, and so
Yeah,
you can use it as it's like the length essentially of it's actually in the node.
cool.
So now we can copy the elements, and then only got 2 copies left to do. One copy for elements to A and one copy for elements to B.
Yeah,
Um, Elements to A. Well, you can probably put a pointer um, from relative index, cursor to relative index, and then we can. This isn't strictly necessary. It's actually just doing balance checking for us. It's copying
yep.
from elements.
Elements to A.
A.
That's nice.
What do you think? Should we get rid of this? This is also just completely redundant.
Yeah, it was basically doing exactly the same. Yeah, yeah,
Yeah, it's just completely redundant. And then, so here we're doing the same thing for B essentially. Um, from B pointer, except here starting at 0, and then going until elements to B, if we want balance checking there, which we don't really need. Um, why is that being, see, this is just being slow again. Anyhow, we don't even need this. It's actually wrong. It should be elements. That's
that's
right.
correct. That's
This,
correct.
yeah,
It corresponds to what we do upstairs, where we shift the existing elements. And what we're saying here is we don't want to overwrite the existing stuff that we've moved into B.
yeah.
So it is nice
And
to
so,
have that.
yeah, that matches this essentially. Or like
Yeah,
these 2 lines match up. It's kind of cool. You can
yeah,
like see how the different things match up. So this
yeah,
one doesn't really match up with that. It's not really supposed to though. This one matches up with this one though. Because then here we're actually copying actually, but these things don't match up, but that's intentional. That's like the spaces we're kind of adding to this node. Because we're
yeah,
adding space to node A
yeah,
potentially, or increasing the
yeah,
count of node A. So node
yep.
A now needs to be um, we need to update the counts now too. So array dot counts A equals
Plus equals elements to A.
cursor dot relative index plus elements to A. Is that good? And then equals, no, it's not that. What is this? It's elements to B to B plus the number of elements we copied, which is going to be I feel like we could have constants for the other two things too.
Yeah.
Like we have them for elements to A and elements to B. We could have the elements like in place, which is just then relative index. Elements that stay,
Yeah.
elements that we need better. I feel like we need better names for these. Um,
Yeah. It would be nice, if possible, that we can do a decrement and an increment so that we're um, not just reassigning the count, but we're removing from it what we shift and what we bring in, adding back. But I mean, maybe it's better this way, the unconditional assignment.
we could do it that way. All we need then is to have, well,
Maybe it's better the assignment.
yeah, I think it's better than the assignment. That sense and that becoming completely in sync with what we just like copied and what we assume.
Yeah. Yeah, it
So
makes
here,
sense.
this is going to be, I can just write out what it is first, I guess. It's going to be array counts. We see now we've like changed this, haven't we? That's why we should have variables for this one.
Yeah.
I want a variable for the amount of stuff we're copying from A to B.
Yeah.
So now it's const like, you just call it const A to B equals counts A minus, and then this A pointer, well, this should be A, shouldn't it? Or do we even want this still? This is A pointer from relative index up to A array counts A. We could now, instead of doing this, we could, if we wanted to, like delete that and then do 0 dot dot A to B, but maybe that's just kind of redundant. I don't know.
No, I like that. I think that's pretty good.
Okay, and then here what we do is we use A to B then. A to B plus B to B plus A to B.
Just to the left there, Isaac, where we say element to be, we must just add an S
Oh yeah, it should
before
be
the underscore.
elements.
Yeah.
And
And
then we can maybe
I
like,
was, I was
go
wondering,
ahead.
where we do cursor relative index less than half. Half is something that we derive from counts plus what we're inserting.
Indeed,
And
yes.
I'm just wondering how we connect that to the first line there where we say A to B, because so relative index we know is less than, we know that relative index is less than counts plus what's coming in. But do we know that, how does it relate to array counts? What if it's,
Well,
can,
relative
can
index
it,
always has to be less than array counts. This is an index inside to a node, and so it's an index relative to a node, so it's always got to be less than the number of items in that
okay.
node.
Oh, of course. Okay, thanks.
No problem.
Yeah,
Um,
yeah, it has to. Yeah. I
so
I
this
was thinking
now, I think,
how can we
yeah,
bind
yeah,
it, But
yeah. I mean, we are kind of already doing that assert just by doing this subtraction,
yeah.
and so there's nothing really to add there. I'm just gonna put a return now. Oh, well, we need to update indexes still, then we can do a return. We need to do something like this, but not. Ooh, this is also wrong, isn't it? This should be plus equals elements.length.
Yeah,
Love when you just like
good
look at
catch.
something. Oh, there's a bug there. Just immediately obvious. Um,
Yeah, good catch.
enter in there. There's less than array node count -1. Yeah, that seems right with the cursor.node less than check. Oh man, there's gonna be fun cases for this when we're doing stuff at the end of the array, maybe. I guess no, it's probably only for this thing. Because now we're checking. Um, hmm. So a is always going to be less than array node count plus. Well, first we need to set indexes for b at all. Indexes for a is already fine, and
Yeah.
indexes for b just kind of needs to be set.
Yeah.
Array dot indexes b has never been set before, so we need to. Here we used to use array indexes a plus half. Instead, we're going to use
Yeah.
equals array indexes a is still a good thing to do.
A plus the count of
but we're
A.
add yeah
Yeah. Array
plus array get counts
dot
a. That's
counts
perfect.
A. Yeah.
And
We
you know what we should assert? Um, this should actually be exactly half.
yeah.
And
Yeah.
b and it counts b should be exactly like half. Let's do some. I'm gonna rewrite this slightly to just do asserts and then assign half. I think.
Yeah.
So I want to do here just assert cursor dot relative index plus elements to a equals half, and then here we're going to assign half, and then assert elements to b plus a to b equals total minus half. We can't have odd stuff here, but that's fine because we were handling it correctly.
Yeah.
3 total minus half. We have to handle it really because you
Yeah.
can insert odd numbers of elements.
Yeah.
And the indexes is just going to be indexes a plus half. That's the same as it was before, because half is the
Yeah.
counts. You can
Yeah.
also use array that counts a here if you like. I think it's actually a little bit nicer.
It's better because then we don't depend on the line ordering.
Yeah.
Yeah.
So here we
That's
do the
really,
counts
really
first
nice.
and the index
Shall we
ones.
do that second assert where we say elements to b plus a to b? Shall we swap it around? Shall we say a to b plus elements to b? Because it's kind of a to the b,
No,
a to b is the first thing we copy. It's the
but
existing
it's the
elements.
second thing in the node.
Okay. Okay, cool.
That's why I had it
That's
this
better.
way.
Okay, great.
I think it's
Yeah.
better. Yeah, it's subtle though. You're right. But I think having it this way will is nicer.
It fits the actual
And
layout.
so
Yeah.
yeah, then I guess here we can just kind of say we can look for is it just if b is less than array.node count minus 1, then we'll update everything after b by element's length. So that's how much we inserted.
Yeah.
Okay, and then we can return. Okay,
Nice.
I think
That's
what we should do
fantastic
now is just do the
how you did that assert and express the counts better. That's really, really good. So
thank
that's
you.
really nice. Yeah.
I think it's now time to do the second thing where half is greater than relative index. And so that means that
Mm.
our relative index is greater than or equal to half.
Yeah.
Which actually I think that's actually the easy case.
Mm.
Let's look at here. Well, do you want to try the new whiteboard that Dynamo has recommended to us?
Yeah. I
Um,
actually
it's
wanted to
CaliDraw.
suggest. Have you had lunch, Isaac?
I have. Have you not?
Okay, I haven't.
All right, we do a
So,
lunch break.
shall we do? Are you happy to do like a 15-minute quick break?
Sure.
Yeah.
Is that
So we
enough for
can
you? We
maybe.
can also take a little bit longer if you want.
No, it's
Um,
fine for me. You've been burning most of the mental fuel, so maybe like
all right.
five past the hour,
Cool.
we can be back
Sounds
on.
good to me. I'll see you back then.
Okay, awesome, cool. Catch you now. Hey, thanks, Isaac. Nice
Hey,
to grab a bite.
cool.
Uh,
Also
I'm
just ate a
so
little bit
ex
more too.
awesome. Yeah, yeah, good. I'm so excited about this. I thought let me come back earlier, even before five past.
Cool. All right, shall we try out this new whiteboard then? We want to now examine the case where cursor relative index is greater than or equal to half. Actually, we could even do it kind of here.
Yeah,
Um, Maybe this is even easier. So let's
yeah,
try that first, maybe. Um, so this could be the case if we have a full first node and an empty second node, and then we want to insert like one element, or just one y. Then I'll leave here like, just the y that's at the end.
yeah,
Um, and so what we do here is, well, cursor relative index is less than half. No, it'd be greater than half then, because our relative index, say, well, it kind of depends on where we're inserting this y2. We could also use the same example as here, but then have the relative index be instead like 4, for example.
yeah.
And
Or
then in that case,
three.
we wouldn't move any
It would, yeah, it would
or
be,
3, yeah. In
yeah.
that case, we wouldn't move anything. We would just insert the two y's here.
Yeah.
Um,
We should just now also we should add a few more of these examples where where there's only one y, because it gets quite interesting about whether you do a whether you copy y into A and to B, or just to one or the other.
oh, well,
Yeah,
I guess we get a zero length slice here, or almost to b would be
yeah,
0 then.
yeah,
Um, and then here you get a zero length slice. You don't do this copy.
yeah,
Almost to a, because that's also it's gonna be zero length to zero length, so
yeah,
that's fine, I think. Yeah, yeah. No, we don't have any index out of bounds there. That should all work out.
yeah. Okay. So maybe shall we do this example where we insert y to relative index 3
So here,
in
you
no,
mean?
in this bottom one that we've got going.
Oh,
Um,
sure. So,
yeah,
um, we expect to get then, well, the total number is still 5, so we still get 2 in the first node and 3 in the second node. That's what we expect, I think. And
yeah,
then you want to insert index 3. Are you doing zero-based indexing or not? So I guess that your zero indexing base would be like that. Is
yeah.
that right?
Uh, that's right. Yeah, let's see. The Yeah, it's four x's and one y.
So that's
Um,
interesting because here you then need to copy you need to copy x's twice and also
yeah,
copy y's.
yeah.
Yeah. Hmm.
Can we get that in the first case as well?
Sure. So it's kind of like a different version of the first case. And so let me
Yeah,
actually just add the relative, the index here
yeah.
as part of the cases.
Nice.
Now we want to try 3 here. Is that right?
Yeah,
And so then we'd end up leaving an x here. And then, well, we have here's index 0, index 1, index 2. Index 3 would actually is not a valid relative index here. It has to be like index,
two. Um,
yeah, well, index 3 would just be inserting the start of the next node then, you see?
yeah,
And
yeah,
so it'd be index 2, really.
yeah,
Um, which means the index relative index is not less than half, which means we wouldn't hit this case at all.
yeah.
Um,
So we would
we then hit the
expect to see
second case.
XX, yeah, XXY, XX. And I think the layout we've got now is correct. Oh no, we'd expect to
No, it's
see,
just the second half is still
yeah,
wrong. This is then
yeah,
index is 2, and so I guess it'd be YYX is what it would be, right?
yeah.
This is very interesting. Is this correct? I think it is, yeah. It kind of makes me feel like we should put the bigger half in the first node though, so we don't have to do this and do those 2 copies. We did the rounding the other way around and put the larger half in the first node, or left the larger half in the first node, then we do less copies here. And it won't affect the other cases in terms of the number of copies, just like how the stuff gets distributed.
Yeah. That's a good idea.
Cool. So let's maybe call half, or we can
We
just
need
have,
to do div seal.
or you can also do total minus total over 2 like that. That also gives you the larger half.
Okay.
I think div seal is actually wrong there. Or no, it's right, but I guess. I kind of want to say like smaller half, larger half. Even though it's kind of like an oxymoron, but I think it helps us here because they are. I mean, half is still like a division. It is yeah. And this is gonna be just smaller half. Then const larger. They don't line up properly. That's sad.
Yeah.
I don't have any idea to fix that there. I'm gonna leave it.
Yeah. Okay.
Then we put a larger half. Then we have to shift all these examples now. And then we also change this. So now it's gonna be if this is less than the larger half. Here we would actually hit that case then, inserting at index 2, 0, 1, 2. 2 is the larger half is 3, so now we do hit this case.
Yeah.
The first copy will be from elements to B is going to be, that's still going to be, well, elements to A is going to be larger half, I believe. Minus cursor relative index. Cursor relative index is going to be 2,
You know
we've
what,
said.
Isaac, maybe what we should just do is say, call it A half and B half. And then in a comment,
Yeah,
just
that's better.
explain, because that way you can straight away see that, and actually we can
Yeah.
even call it A half, or we can even call it A count and B count.
Yeah, it's not. It
But
doesn't even need to be half. It just call it. Well,
yeah,
that'll confuse me because I think that makes it then easier to mistake that for like array.counts A if we call it A
okay,
count because we use that elsewhere as array.counts A below. I think.
yeah, okay, cool.
I think this
And
is.
then yeah,
No,
cool.
no.
And then we can
My.
just explain in a comment why we bias it towards the first.
Yeah. And I want to understand this a bit better and walk through this second case with the
Yeah,
new adjusted halves to make sure everything still works out.
yeah,
So we have A2B is going to be counts A, which is 3, minus relative index, which is 2, so that's 1. It also makes sense with what we see here in the example. Elements to A is going to be 3 minus 2, which is 1. Okay, yes, this is also wrong. We also want this is what we're going to end up with
yeah,
the new A half is larger thing.
yeah,
Elements to B is going to be then 2 minus elements to A, which is 1, which will also be 1. So these are all 3 of these are 1. Then we've got B pointer, which is elements to B. Well, we copy from A pointer to 1 element. So that's this element exactly. We put that at the index 1 of B pointer, which is here. That looks good so far. We copy 1 element from elements into A at index 2. That's that. Yep. And we copy the rest of the elements, which is 1 more element, to B pointer at the beginning. So that this all works out. That's nice. Cool. And then this case, where we do y equals 3, let's make sure that actually does fix the problem. And then we don't do 2 copies then or 2 x copies, and just leave that x there. So we now have relative index of 3, which is the larger half is equal to 3. So I'm not even sure. Should we be hitting this case when we have an equal? I think not. I'm not sure yet.
We can always explicitly work through it and see which side it falls.
Yeah, let's try that. So let's try this branch for this. Say if this was an equal, that would mean that this a to b can be 0.
Yeah. There's actually another case I wanted to try also, where I think we've maybe got a to b wrong. So imagine if we have the node with only a single x, and we want to insert 4y at relative index 1. So we have a single x.
Well, relative index 1 wouldn't be inside this node though. That's actually invalid. If you only have a single item in the node, you can only insert at relative index 0.
But what if we add the last node in the array?
We allow insertion past the end? Thought we didn't.
Yeah.
Maybe I'm wrong though.
We do because you can append to the last node. So what'll usually happen is that we'll end up jumping into the next node and inserting at the beginning.
So we say this here: the absolute index argument is the index of the new element will take and may therefore be 1 past the end of the array. Then we assert the absolute index is less than the element count max. Isn't that contradicting this a comment though?
No, that's just saying that there are 2 different things. So element count max is something statically worked out.
I see.
Yeah.
Yeah.
So cursor for absolute index is going to find, normally it will jump to the next node, but in this case it's the last node.
Right. Yeah, I remember this stuff now.
Yeah.
We target the index 1 past the end of the array. Yep. We definitely need to handle that.
Yeah.
And so, yeah.
But we're doing pretty well. Like I think we're cracking it, you know.
Yeah, we're chipping away at it for sure.
Yeah. Yeah. So shall we work it out? Over here, x. There's one x. We want to insert 4y, and we want to insert it at relative index 1. So what do we expect after the x? So
we have larger half is going to be equal to, I think. So we have here then larger half is equal to 3. So we hit this branch. Then a to b is going to be right at counts a minus cursor relative index. That's going to be what? 1 minus 1, which is 0. But that seems right.
Okay, cool. That's good.
Elements to a is then larger half minus cursor dot relative index. That's going to be then 3, which is larger half, minus 1, which is 2, which is perfect. Elements to b is then the inverse of that, which is also 2. And so yeah, you get the right thing.
Okay, awesome. Nice.
Yeah.
And I was just wondering, cool, I was thinking we should find another name for A to B, because A to B is kind of, it's the same as elements to B. It's just that elements to B is the new stuff we're inserting. A is the existing stuff. So I was wondering something that lines up, but maybe we can call it existing to B.
Okay. Yeah, that works too. I like that
Yeah,
more than A to B.
yeah,
Um,
and it
that
lines
even
up.
lines up. Wow. I'm impressed.
I had a feeling it would. I hadn't calculated it all the way, but in my head I thought it would line up. Yeah. Okay.
Nice.
So,
All right. So I think we just need to look at the cases where this isn't true more carefully now and see what we want to do there. And so
yeah.
we already had this one, I think, where we have y and we're inserting at relative index 3. Oh, we also need to examine 4 here because now I've realized that you can actually have one past the end. That's valid. So we need to check that as well. So yeah, this is actually the first case, I believe. So I'm gonna put this one up here. Okay.
Yeah.
So we insert y to relative index 3. That's 0, 1, 2, 3, and that's not less than the larger half. Larger half is 3.
Yeah.
Um, so we actually want to get out here now, though, is not that, but rather this. So we don't have to copy that x.
Yeah.
Um, does this code work for this? Because then if so, then we can make this less than or equal to.
It
Um,
does.
that-
Yeah.
it does. I think it.
Let's
Yeah. Let me just go through
let's
it. Yeah.
step it through. Yeah.
I think just finding these three constants is enough for us to be happy, because we know what the
Yeah.
copies do now,
Yeah.
and we know what these constant means. And if these three constants are like work out correctly, then it's all fine.
Yeah.
Um, so existing to B is going to be counts A 4 minus relative index, which is 3, so that's 1. That's perfect. That's this.
Well,
Elements to A is larger half, um,
which
which
will
is
be
3 minus
three.
relative index, which is 3, which is 0. Okay, yeah, it does work out perfectly. And so this is then
Yeah.
1. And so, yep. Sweet. So this can be less than or equal to.
Yeah. Nice. And then, do we have any? We don't have any bounds overflow in our slices with our zero length
No.
slices. Uh,
Well, hmm. We do start slicing at A, but A's gonna be yeah, no, that all works out. I'm pretty sure. If it's not, we'll get an
yeah.
insertion failure, and so we can fix it.
Yeah. Yeah.
But so what's the case in which this isn't true now? When relative index, I guess that's the case here where we're about to do, where we have um, relative index of 4. We want to insert y to 4, I guess.
Yeah. By the way, these like this simple notation that we've got going, yeah, Remzi Apache Dussault and his wife, they've got Andrea. They've written a really cool operating systems textbook called O-Step, like operating systems in 3 easy pieces. And in it,
Yeah.
they use these kinds of examples all the time as like a principle to show that if you use small little example data, it really helps to understand the problem. Uh,
Yeah, this
so
definitely been helping me.
yeah,
I like just having it in the text editor too. It's been a little bit more precise than the whiteboard.
yeah,
Um,
and it's quicker just to draw up the scenario. Uh,
yeah,
so maybe we can call this the RAD method, like short for Remzi
yeah.
and Andrea Apache Dussault, the RAD method. Uh,
Cool. This isn't right anymore, is it? We want it to be this now on the output. Yeah.
yeah,
And so, yeah. So this is the case now where relative index is less than or equal to larger is greater than larger half. And so that
I'm kind
means
of
that
wondering. I'm wondering now how we solve this in our normal insert path, like where we've got a relative index outside the node. How did we just get that
um
right?
well we just kind of we see that the relative index outside the node. I think we only allow that at the very last node of the array.
Yeah. Would you be okay
Um,
just to go
or,
and we can go and take a look?
yeah, yeah. So this is the place where we handle that. So we only actually return this if a node equals array node count -1. So this only happens
Yeah.
for the very last node of the array that we allow this.
Yeah.
Otherwise, we assert that it's strictly less than the array node counts.
Yeah.
So that means this will only be returned if it's the very last node in the array. And then how we handle that is that we just create a new node if it's full,
Can
which
we
is
just check
what has
how?
to be the case.
Shall we check in insert element where we do that? Because I was kind of surprised.
It's in, what's it called? Insert node. This one, split node. Nope, split node of full. So we'll get cursor for absolute index. This may return us a relative index actually greater than the node count. But it should only ever do that if the node is
For the
already full.
last.
And so then we just split the node and keep on going. It will only return you a relative index out of bounds if the node count of the very last node in the array will otherwise.
So
We
I
probably
think
tighten this
like
up with an assert.
yeah, yeah. So here, if I understand correctly, we'll get the cursor to the last node. The last node still has spare capacity. Um, okay, it doesn't have spare capacity. Okay, then we will split the node, and then we will.
Mm-hmm.
So in other words, what we could assert is that the relative index by the time split node of full is done, that should always be within bounds. That's what we're saying. Is that right?
No.
The
Well,
I
actually,
think
yeah, maybe. I think you're
by the
right.
time by the time we get out of split node of full, the cursor that we get will um,
Hmm.
oh, okay, so I
We
think
can
that's
insert
actually
here.
we don't need that anymore.
Should we like test that real quick?
Yeah,
Just get rid of this check.
yeah,
See if that passes our test still.
yeah.
I think I won't do anything that won't. I probably got some stuff that won't compile right now. Let me look. Actually, these things aren't referenced though, so it should be fine. No, undeclared identifier, of course. 153 node. Wonder how many more of those we have. 168.
B
Um,
half. A half. You know what we should do? We've got an A half and a B half. All we need now is a Gandalf, and then we'll be. Then
Doesn't
we can do
now.
another. We can do another Zig show time.
Uh,
Uh, if Larice will have us back.
A half, B half. Okay. That should now compile, I think. Oh my gosh. Why is it
168.
compiling this thing? Oh, you know what it is? Because we use. Our test was not going to pass right now because we already refactored this function to do the other thing.
Okay.
Should, we should maybe like
Yeah.
make a old version of this that does
Yeah.
the
Yep.
classic
Yeah. The
version.
John Carmack method, where you just copy and give it an extra name.
It's just temporary.
Yeah.
Um, I think the old version of this was just a for loop, right? For
Hey,
elements.
Hey, Luis, what's up?
Hey,
We were
Lars.
just talking about you. I don't know if you heard the Gandalf comment.
E and I, and then we're just gonna do array dot insert element node pool absolute index element. Yeah, node pool absolute index plus intcast u32i element. Here's E.
So I'll explain the joke for
That's
Luis.
recompile.
So we've been splitting these segmented array nodes, and we have to split them into halves, but now we're dealing with smaller halves and bigger halves, so we ended up renaming them A half and B half. And then we realized, hey, we just need to have a Gandalf as well. And then maybe you might have us back on Showtime. Anyway, so that was the joke.
Yeah, so this decision has failed, so we probably need to look into this.
Okay. So you mean maybe our tests didn't cover that?
Yeah, I think our code might be right still. I think it's not necessarily wrong. I think we are just not understanding
Add it,
that entirely.
can add it to do. Like,
I wanna understand it now though.
yeah.
So, and no, that's not the case though. That this will return a cursor to the current node, because if we split the node, it's going to be empty,
I think that's
right?
why
We
it
just leave it
fails.
empty.
Yeah.
Oh, well, we split the node in half. Or absolute index is still past the end. That doesn't change the fact. We don't actually insert the new element yet, so our absolute index is still past the end. And we can also, yeah. So, yeah, this is all that was right before. That assert can't be any different there. Um, Let me copy that back from here, I guess.
Yeah.
I can explain it just a second too. Let me just fix this up first. Okay, so in split node of full, it's very possible for us to hit this path and not split the node if the cursor is past the end of the array, like past. It doesn't. The last node doesn't have to be full for this to happen. This is just if you have like one element in the last node and you want to insert a second element after that element, we have to have this index past the end, right? And
Okay,
so
of
in that
course.
case, you
Yeah.
won't split the node either.
Okay.
Um,
Yeah. Yeah.
that can always be the case in the last node, no matter how full it is. It doesn't mean that you're going to
Yeah.
split the node for sure. And
No.
also splitting the node won't even change it because it doesn't insert a
Yeah.
new element yet. It's the index in the new half full node will still be past the end as well.
Yeah.
Um, we just need to handle
Cool.
that case properly here.
So
Um,
in insert element, have we enabled that assert again? Did we go back
yeah,
to
I put
what
it
we had?
back.
Okay, cool.
So now we
And
can
if it
test the test
is, yeah,
again.
cool. If it is, then where do we actually handle it? If it, then we say,
What do you
oh,
mean?
we actually, oh, we don't really mind. We just compare against node capacity.
No,
That's really what counts.
we don't really mind at all. Because we know that we have to have space for it to insert here because we now split the node if
Yeah,
we needed to.
yeah,
And so we just insert at it. Yeah.
yeah. Okay,
Yeah.
cool.
And so back back to here then I guess.
Yeah,
Um plus elements to A equals A half. Yeah, so now I guess looking at this case, I guess, and we can insert index 5 then. Or we can try, well, let's try maybe first here, inserting an index 3. See if that works out. I think I want to try that one first. this will then exercise the code we already have.
Yeah.
And say if this happens to be the last node, what we want is this should be an x, and then we should have two y's here. Like if we handle that correctly. So existing to be, we expect it to be 0 now. That's going to be counts minus index, that's 0. Yep.
Shall we,
Elements to A is going to be
can we add a
3
new line
minus 3 also 0.
can we add a new line just before elements to A so that they set a little bit away from existing to B?
Sure.
Like that, yeah. Yeah. Cool.
Then elements to A is going to be also 0 because you've got 3 minus 3, and so elements to B is then 2. That works out.
Yeah.
Cool. There's nothing special there, I don't think. Then if you have 4 things and we insert at index 4, like we just added here. We haven't really done this one yet, though. Actually, we do expect this to be handled like this. And so in this case, cursor index is not less than or equal to half. This may be the only case in which it isn't.
Yeah.
And so what we want to do then is copy from exist. I feel like, yeah, because we can't use the same copies. It's a different copy now. Yeah. So I'm going to copy this case maybe. Well, I think it's just this case that that we have so far for this second version.
Yeah.
And write out the code for it now.
Yeah.
Else. Just a nice little cryptic example.
Yeah. But you know what, Isaac, I think here what will happen is we would, again, I'm getting confused with the previous
yeah, because the problem is the y ends up after the x. Copy x to the start of node 2 now, which we don't have any way to do in here. Here, basically, all we set based on the conditions and the state of things is these 3 variables, and this stuff just happens. But there's no way to set these 3 things in a way that you get this result. That's why we need the second case, where we can't really assert this. We can just assert that it's greater than half in case we change it up there. Maybe, I don't know.
Yeah.
Is that even worth doing?
Yep. Yeah.
Just
definitely.
to make sure, because now it's kind of far away from this if condition, so we might as well like double check that we don't mess up the code in the future.
We should also have an assert where a half is greater than or equal to b half.
A half, yeah. Okay, and now I think it's going to be existing can be can still exist. This is still good, I think. It might even be calculated the same way, or maybe not. No, this is now going to use a half. It's going to be a half minus counts, or what's this going to be? It counts a minus a half. Is that right?
So so we've got 6 elements. There's 4 x's and 2 y's.
It's relative index minus a half is what it is.
Yeah.
Yeah.
So
existing to be
a half is going to be equal to 3.
And relative index is 4, so that'll give us the 1x we copy over. And then all of the elements. This is actually the way simpler case. This only has 2 copies. To the start of B too. So B pointer, and then A pointer. Starting at relative index. No, where are we starting? We're starting at a half.
Yeah.
Dot dot, and then 0 dot dot existing to be. Then the second copy is going to be just from elements into B pointer. And B pointer B elements. That's all we
Maybe
got.
we should
So these ones.
maybe we should slice on elements as well.
To where? Elements at length?
Can't really here. Yeah.
We can do some assertions though, if you like. You can here assert.
Okay.
Or maybe it's better to do this up top where we have calculate existence to B, then we do some assertions, then we do the copies.
Yeah.
Assert elements dot length plus existing to B equals B half.
Yeah.
How's that for one?
That's great. The beginning
actually, we
where
can
we
do
say
that.
elements, just need a that's it.
We can actually do that down below where we do this, because we still need to do this part. And so maybe we should do that those assertions down below like we do up above. And so this is the B half one, and then we can do A half. Well, A half is really just going to be, well, let's do it in terms of existing to B. It's going to be counts. The like array dot counts A.
Minus existing to B.
Minus existing to B. Yeah, that's because then we're like kind of like have the full circle of dependent things here. So we've got relative index A half and counts A.
Yeah.
And then we're relating them through this temporary. Cool.
Yeah.
And then
I think
we do the same thing
really
here
nice.
with A half and B half. And this is also going to be the same. This is also going to be the same. So we can actually unify this stuff like outside of this if statement, I think.
Yeah. That's cool.
Cool. Yeah, so the code is going to get a little bit more unified. That's nice.
Yeah.
We don't have so much duplicated code. And it's good we do the asserts before we return them here too. These are dependent, and then we use A half and B half because those are the same for both of them, both paths. Then we can get rid of this stuff. This is now out of date.
Do we want to hoist those asserts up to the top of each branch?
Sure, we can. Maybe they do make more sense there then.
Yeah. Then we're kind of explaining the branch as well.
Yeah, so we just make our constants, do some asserts, then do the copies. Yeah. And then we set the metadata at the end.
Yeah.
And what do we want to do with these examples we had? Do we just delete them now? Leave them until the tests pass?
We should keep them. It's nice for future reference. We can just try it and explain, maybe where we say 4 on the right, we can just say relative index equals 4. Or we can say insert y at relative index. Yeah, elements y.
Y and then x.
Yeah, that's it.
4. And maybe this should go on like the previous line. I don't know.
Yeah. And we can make it yeah, that's cool. And then shall we move that to the top and then move that other assert just down? So we keep the comment like at the top of the branch. Yeah. Like that. Yeah. And then the others we can show also in line.
We might not need all of these. There's a lot of them. Which ones do we want to get rid of? I think we've now duplicated this one. This is the one that's duplicated below, so we can get rid of that one right away. I think we want maybe like one of each y length. So we've got like a y length 1, next 3. Definitely want this one. I want to keep.
Yeah.
I think I want to keep this one too. That's like
Yeah.
a case where the almost a is 0, and then that's where it's
You
split.
That last one is
And then
the
also one
motivator
where element
for
were
why we
beta.
want to.
Yeah.
Yeah, that last one is
I
why
think
we
we
want
want
to
to get rid of
bias the
these two.
division. Yeah.
Yeah. I think we want to get rid of these two. These are like two basic cases. Um,
Yeah. The second one is nice
then
because it shows you with y on both sides plus x on both sides, which we don't otherwise
okay,
have. Yeah.
let's just drop the first one then maybe.
Yeah.
And the other ones are all fine to keep.
Yeah.
Um, so let's. Yeah, that's not gonna work. That's the best way to do this. I can do it like this. There's got my 4 cursors now. All right.
Yeah.
Um,
Nice. Are you ready?
are you ready? Maybe. That's actually gonna be gone. Okay. Ooh, got a little messed up. To insert.
I think when we announce these streams on Twitter, we must just talk about the awesome multi-selection that people are going to witness
Yeah.
if they come and watch.
You don't want to like hype it up too much though.
Okay, okay, yeah.
There we go. And
Yeah,
then, because it will be like kind of awkward. But the great part about this in Cocoon is that this is iterative. Like you get immediate feedback instead of
yeah,
having to like write a macro in Vim and then like adapt it to your feedback. So in Vim you like never would write a macro, or at least I would never write a macro for this thing because it would be impossible to
no,
get right.
yeah,
Um,
yeah,
like thinking
yeah,
enough ahead for that. But here I can just kind of like fumble around until they all end up right. And
yeah,
it works out pretty well.
yeah. That's very cool. Can we test it a bit more, the multi-select, and rename to insert? We can make it like the second branch, just call it elements.
Oh yeah, I forgot that I called it that time. Um,
Yeah, easy,
I
easy peasy.
think I
Yeah,
also added comments here, didn't I? Um,
yeah, yep.
yeah, cool.
Nice.
Nice.
Shall we put it into that the branch?
Yeah, we should.
Yeah, nice.
Okay.
And then I
Uh,
was thinking, um, maybe tomorrow, like we can do. It would be nice if where we do the division, just to do it as a ceiling division, because that way we can keep the order the same. We can have a half defined first, and
we can also just do that
because
now if you like.
yeah, okay. I was thinking we could maybe run the test if we get to run a test already.
Uh, yeah,
I've
well,
got to.
we can already run the test now if we like. We're done with this now. We can test it
Yeah, yeah. Let's do that.
and just see what happens.
Yeah, yeah.
Um, I just need to rename this one and just call this one old now. Um,
Yep.
oops. And then it's going to compile and run right away, right? And pass all the
Yeah,
tests.
yeah.
At 182,
Nice.
man, it's the same error it's repeating the same error like 10 times.
Yeah.
Interesting. I wonder why it's doing that. Interesting.
Hmm.
182. Why is it doing that? Uh, that's gonna be close enough. 182. Cool,
Yeah.
it's less than new capacity. Um,
I was thinking maybe we could come and look at this case and see if it can't um, dissolve into
yeah,
the
let's
other
get the
two
test going
as.
first.
Yeah, 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 yeah. No,
I
yeah,
understand the ration. I'm with you
mm,
there. It'd be awesome if they all
yeah,
like nicely went in one case, but
yeah, yeah.
I'm not
I'm not
confident we can do that
suggesting
without breaking
right.
things.
I'm not suggesting right now, but just long term.
Yeah, yeah. All
Yeah,
good. Um,
yeah.
So total is a U size for some reason, so we should make that not a U size
Cool.
by doing this.
Yeah. That's it.
Where are we at now?
Line 273.
There's another one. Okay, yeah, I did down here too, didn't I?
Yeah.
Yeah. There's definitely some more code here that could be unified. We just need to. This loop is what I'm looking at right now. This could definitely be unified, and I think probably these parts as well. But let's come back to that in a second.
Yeah.
Okay, so it looks like we ran it and we got an integer overflow because elements.length minus elements to a somehow. Yeah. How is elements to a like greater than elements.length though? That seems really bad.
Yeah, it does.
Let's go figure that out.
Yeah.
A half minus cursor.relative index is elements to a. So, but a half is how is that calculated again? That's total. Total is going to be. So let's say elements.length is 1, and let's try and make this 2. So make a half 3, cursor.relative index like 1. Yeah, this just seems wrong.
Yeah.
Something's wrong here.
Yeah. Oh, it could be because we allow it now to be less than or equal to.
Oh, yeah.
But I don't know.
Well, yeah, I think that's not the case. No, that's not the case. I think the case is when relative index is like 0. Like that, for example. If we are considering relative index is 0,
Yeah.
and then a half is 3, and elements.length is 1. It's just wrong. We've done something wrong here. I'm not sure how to fix it though.
Yeah.
Um,
Should we
well, I
work
think
out
we
that
just need to.
scenario?
Honestly, I think it will pass the test if we just use saturating arithmetic here. Whoops.
Mm.
I just closed that buffer. A half. I think we just need to. Well, elements to A will also be wrong though, so we can't just do that. That's not a fix. Yes, let's work out the scenario. I think you're right. We just need to do this thing. Let me copy and paste this one maybe.
Cool.
I think it's the same thing as this, but with relative index of 0. Let's try that.
Yeah.
In this case, we want to see. Yeah, look at this. So here we want to see. Yeah, we don't handle this at all yet.
Yeah. So we want 1, 2. Yeah. So we've got 4 x's plus 1 y. So 2 x's. So elements to a is a half. A half will be 3. 5 divided by 2, ceiling division. A half is 3. 3 minus 0, elements to a is 3, which is wrong.
Yeah. And so I think we're missing an if statement. I think we're missing a branch of this if chain. I think there's another case we need to handle, which is whatever this one ends up being. So how do we detect this compared to this case?
I think what it is the question. You see, no. So far in the other scenarios, we've had cases where y is in both nodes. We've
Yeah.
also had cases
Now
where
we want
y,
to.
where y is in the latter node. And this is now a case where y is in the first node
Only.
only. Yeah.
And we need to shift x's within the first node. That's the case. That's what we're not handling at all right now.
Yeah. Yeah.
If x's need to be shifted inside the first node, if we just don't handle it all. What other
Yeah.
cases are we just totally missing?
There can actually be, um, yeah, that's the last one where x has to be shifted in the last node.
Yeah, so this one is where x needs to be shifted from the first node to the last node. So yeah, so okay, I think here's the good way to think about it. So this one,
Yeah.
this branch is when y is in the middle of the x's. Then we've got here where y is at the end of the x's.
Yeah.
And then here we need y at the beginning of the x's for this, perhaps. I'm not sure if that's totally right though. That might be missing some edge case. I'm not sure.
Yeah. I think there's another case where y shifts x's. So basically the only case we don't have is where x's shift into the next node, but they also shift in the node they're in. That's what this is.
Yeah.
And we haven't run into it so far because our examples have been limited thanks to the RAD method. So if we had done like 6 elements in a node, we might have hit it a bit sooner. Because then you start to see the half
Maybe.
point.
Yeah.
At the moment, it's too easy for stuff to go all the way across, but not be shifted in the same node.
Yeah.
Uh, but we're getting
So
there.
definitely, it's not easy though. So I think
Yeah.
what we want is now another case where we say if cursor.relative index plus elements dot length is less than half, or what does this look like?
I think it's got to do with the count of what is the existing count. If the existing count is if relative index is going to be before the existing count and existing count or so relative index is before half and it's also before the existing count, then it means we need to shift some of the existing elements within the same node. So I think we basically need to have existing to A, existing to B. We need an extra copy sometimes.
This seems to a okay. So do you think we can add this to this case then?
I think so, yeah.
With an existing. I think you're
Yeah,
right. Yeah, we probably can.
yeah.
Existing 2A, and then that copies. They'll then copy it. Oh, is there a case? Maybe I want to look at one more case before we do this.
Yeah.
Oops. Like a case where we have a few more elements, maybe to make these easier. Let's have like 2 more x's,
Yeah.
and then have 2 more slots here. And I want to put x's before and after the y in this first block.
Yeah.
Like now we have here 6 in
X's.
total plus 1y is 7 divided by 2 is gonna be 4 and 3. This is what we expect then with one more. This should be, is that right?
Yeah,
And
there
we
should,
might need one more underscore still.
and there
There
should
we
be
go.
another X. Oh no, that's correct. Yeah, that's correct. So here the
Yeah, and then here
halfway point is
relative index
4.
is 1.
Yeah. Yeah. So the relative index is
Okay.
before the halfway point.
And so then the order is going to be the things that don't move, then elements to A, then existing to A, then
Yeah.
elements to nope, now we've got a problem because now elements to B that can't come after. Well, if I think in this case we've got to assert the elements to B is 0 or something. Maybe we just want a whole different branch of this if to start with at least and see how that goes.
Why do we need to assert, Isaac?
Well, I was trying to like list off the order of how these things get placed, but then on elements.b to B, if you have existing to A, then you can't elements to B must be 0, right?
Yeah, 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 yeah. That's got to be 0.
And if you have elements to B, like the converse is also true, or the contrapositive, I forget what that is.
Yeah,
Inverse.
yeah. I think we could handle it here. So if all the elements are going to A, then elements to B must be 0, and if yeah, and the other way also.
Yeah. We just need to assert that 0, but in general, like the order would be then we have existing to A, and
Yeah,
then existing to B. And that'd be
yeah,
kind of one path. And the other option is then to have, like here, where you then have just the ones that stay still, then existing to A, or elements to A, then elements to B, then existing to B.
yeah.
So what is existing to A going to be then?
Shall we shall we leave it as a cliffhanger for tomorrow? I've got to head
Okay.
out.
It is now 3 o'clock in
Oh,
the afternoon, so yeah, before I take
yeah.
it. Yeah,
Awesome.
this is gonna be fun. I'm gonna keep thinking about this. I think just because it's gonna keep bouncing around
Yeah,
in my
yeah.
head a little bit. But yeah, I'll be
Awesome.
happy. I'm excited to come and figure this out tomorrow. Um,
Nice. It looks really like approachable, the naming of the things and the copies.
yeah,
It's coming out really nice. Yeah.
yeah, it's tricky stuff. I mean, I said this was gonna be tricky. I think I was not wrong, but I think we're doing a pretty good job managing the complexity here. Um,
Exactly. Yeah. 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 It's definitely tricky. Yeah. Yeah. But
and
it's
but
gonna look
here when we're
at the
now
end of it, it's
reducing like the copies are gonna be like so much better. Like instead of doing like
yeah.
20 copies to insert a batch, you're gonna do like 4 maximum.
Yeah. 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 It's a tricky problem to solve, but I think we've come up with a simple solution. Yeah.
Yeah, we're not quite there yet, but we're getting there. We
Yeah.
solved like at
We
least
get
half
it.
of it.
Yeah. Yeah. No.
We think.
Awesome work. I think you
All
deserve to
right.
sign us off today.
All right. The Tiger Beetle sessions, Monday the 31st of whoa. The Tiger Beetle sessions, Monday 31st of January, session 14. Signing off.
Cheers, everybody.